So good morning for everyone. So we are just going to wait for 2 minutes, 2 to 3 minutes, just for the other people to arrive. Just a moment. De Oliveira. He's from the Universidade Federal do Espírito Santo. He concluded his PhD under the supervision of Martin Mackler and co-advised by okay, Shirley Hu. Shirley Hu. Okay. So Renan, so we'll have 15 minutes more, 5 minutes for questions. So you may start now. Thanks.
So, hello everyone. I think you can hear me well. If not, please let me know. So, the subject of my presentation is the LastGuru database, and I will talk about this database and why it's important. Okay. So just to give a motivation for this, the data that we built together. First, we were interested in where can we find the data to test many analytical models. So we know that there are a lot of data available in the literature, especially for if you're working on a survey, but you mainly restrict to the survey that you were working on, and maybe there is no data available there for you. So there is a necessity for exploring the observational data from strong lensing systems. And of course, we're interested in studying the systems, and we can use might use real data in machine learning applications regarding only simulations. Because most of these strong lens systems are rare systems, and maybe there are real data, and we might train a machine learning model there for maybe do a regression or a classification problem. For this database, we're mainly focused on images from Earth, mainly because of the LSST. And this is our main motivations, because if you look to the data available, you might find a high resolution for many strong lens systems from Hubble Space Telescope and from James Webb, starting from James Webb since last year. But images from Earth with real good quality, it's still we're lacking of this data. So actually, there are many lensing catalogs available in the literature. However, most of the information is not always available. Since this information is not available, this might be a problem for us, because in some cases, we may have tabular data from many lensing parameters, but the other catalogs, they provide imaging cutouts, but not both information combined. And this might be an issue. So the content of my presentation is where I briefly show the data gathering status. I present some cross-matching data with other catalogs available. We perform a photometric cross-match and then a spectroscopic cross-match. We also build a consolidated catalog that combines all the information together. And also we look for images from wide field surveys on Earth. And finally, I present the whole structure of the SL framework and the database we built, and some concluding remarks. So these are pictures from the database, and I will present something later. So for the data gathering process, so we perform an exhaustive search for strong lens systems from the literature. So we search for many articles that performed serendipitous discoveries, other articles that they use spectroscopic observation to find strong lensing systems. And then we also look for other papers that perform the same technique, different techniques in the sublimeter, X-ray emissions, visual and automated inspection. Actually, this visual and automated inspection is really common because people built many arc finders, for example, and most recently, automatic inspection using machine learning techniques and other compilations. So I think yesterday people from the group present many data that use data from other compilations of many strong lens systems. So we look for that. And also we search from data available in master lens database. And finally, we search for cutouts for many objects. So we got the images from, I will show later, from many systems. So for this database, we define a unique identifier called JName. Basically, this is very common in astronomy using hour, minutes, and seconds for the coordinates. It's based on the coordinates of the systems, and we use this key to match with the imaging cutouts. And so all objects in the database we had to name with the same JName. So for example, here is the system. It's from Masterlens database, for example, and then it has all of these green dots. You have the different coordinates for this is the main galaxy, and this is the arc. So we combine all this information together in a single average of the coordinates in the center in this thing in the center, and we assign this as a unique value for the database. With this, so we use a matching radius of less than one arc second. So all the objects inside of this 1 arc second, we assign the same JName. So if you have a matching radius between 1 to 10 arc seconds, also have the same JName, but we also keep the provenance of all the coordinates together. And if you have other systems outside of this matching radius of 10 arc seconds, we classify as a unique system. So actually, one question that you might ask, how can a different system that has less than 1 arc second and 10 arc seconds? We also keep the provenance of the system type. So we gather many information, the positions and the redshifts. Okay, so I think I'm supposed to have other slide here, but basically we classify the systems that are inside this radio and the outside of this radio of 10 arc seconds. This choice is arbitrary, but it's just choice to start to gathering all the information together. But this is open to improvements as well in the future. But the main motivation to gather around the objects in the single image is to have the same cutout. I will show later. So we gather all the information regarding the position of the systems, redshifts, and system types. So for example, galaxy, and cluster galaxy kind of lensing system. We also kept the provenance of the Einstein radius size, the velocity dispersions, very used yesterday, and magnetism of the system, and the grading. So for example, if you have many systems that were graded for, this is likely to be a strong lens system, I will give it grade A, or for example, arc findings that show the probability to have strong lens systems. We kept the provenance of this data. Always keep the information. And so the first data that compiles information from any, only from data from the literature, it's around 31,000 objects. For the system types, we have the single lens galaxy. This means that we have only a single galaxy in there, and the system is classified as a galaxy. Non-single galaxy means that you might have a group of galaxies. So, for example, a small cluster. We assign the same JName, but it's not necessarily the same object, but it's a non-single lens galaxy. That's why. And if you have a non-single lens galaxy merge, it's the merging of these objects in the range that I mentioned earlier. So again, we gather all this information together. And with this catalog, we cross-match it with other data available in the literature. So we search for spectroscopic surveys, most from imaging surveys in photometric data as well. I'll show, so this is our the spectroscopic photometric, surveys that we search for the object. So we try to cover most of the whole sky using only data from Earth. And then for spectroscopic cross-match, we for show we only showed in 3 ranges of spectroscopic cross-match. So this one is from a deep spectroscopic searches. The sky is small, but we have the medium, and we always try to find at least the spectroscopic redshifts from this object. And this is for the whole sky service. Right, so we have a catalog from the literature, a catalog from the spectroscopic cross matches with other surveys available. And we also gather the information together in a single catalog, because we want to merge all of this data together to obtain a unique value, which is very convenient for the user. And also we remove any consistency between the data available, because sometimes in one survey, they provide one information, but it's not necessarily correct. And we also create a hierarchy to decide which value should be used. So in principle, if you want to know the information that came from which paper, you have this information available. And we also kept the information from other previous as well. But with this catalog, you can do a quick search on these objects. So for example, here we merge all the data from mostly from from the redshifts. And then if you find follow this hierarchy, we have all of this information together. Always keep where did the data come from, if the what's the spectroscopic the redshift type, and so on. Okay, so this is from the tabular data. For the images from wide field surveys, this is very useful for modeling the lens in the source. With this data, we can improve strong lensing finders, and this data can be really useful to LSST. For a start, we get at least imaging surveys with 100 degrees squared and sub-arc second scenes, because we want to have images with high quality. And we have this data in many photometric bands, and we obtain cutouts in 20 arc seconds in 4 arc minutes in a fit format. So 20 arc seconds is very useful for Galaxy scale lenses and useful for machine learning model applications. And 4 arc minutes, it's cluster scale lens, which is very convenient. This is why it's very useful to, for example, if you only use images in the 20 arc seconds like this, you might classify this very nice Einstein ring. But actually, if you see the environment in a more huge image, you see that this is our galaxy. So this is very interesting to gather this information. Here is the footprint of the surveys that we get the imaging cutouts. And here, just to summarize, for example, the Galaxies survey has 28,000 images available, and then here it shows the intersections. So as you can see, there is only at least 217 systems that have images in at least 5 imaging surveys. So this is one of the important things. Another, we process the images using different methods, and we use this tool Trilogy to also, so we provide to the user the fixed images, but also a processed image, because you can get quickly see the details of this information. This is very useful for applications such as follow-up observations. And here just an example. So this image is this object seen in different surveys, and all of this information is available in the catalog. And also, depending on how you combine the image, you might see some, for example, this you might think it's a perfect Einstein ring, but it's not, is only an artifact of the image processing. To summarize, this is the main overall of the SLComp framework. And with this, we think we can use this framework to create many data versions of this catalog, always getting new data once it's available. So we dubbed this, the first data version as less than before rubbing, and as known as less brew. And just to summarize some numbers, I'm almost running out of time. I'm finishing my presentation soon. So we have 5 catalogs, one data from literature, cross-matching surveys, create catalog, merging all data together, and a catalog for imaging cutouts. We have all of these image systems classified as galaxy or clusters, and we have this information for redshifts, source in lens redshifts, and almost 1 terabyte of data available and processed images, which is very useful. Just concluding remarks. So we create this database, we compile all of this information from the literature. It might have a very important to preparing grounds for the LSTST for please do this kind of science. And it has large machine learning applications. For the future, we want to include more data from other surveys, for example, Delve and Hyperspring can Legacy Archive. Of course, incorporate data from Rubbing, tagging. I think this is the topic for the next presentation, and using this data from many machine strong glazing applications. So before I finish, let me show quickly this Thursday, we have a hands-on activity. So I will share the materials with you later. I think I switched my screen again. No, I'm not sure. Can you see my, okay. So this is the repository in the GitHub. I will share it with everyone. So we prepared this dashboard that combines the information together for the user, and you can quickly access the, at least see the data here. And then we also prepare a system that you can query the data, and so you don't have to download all the database together. You just only download what you need. So with that, I thank you. Or if you have any questions.
So thank you, Renan. So, questions? Yeah,
If not,
the question
okay.
just a moment.
Thanks, Renan. In like places where that are missing data, like systems that are missing data, is that like possible to like get that back from like the cutouts to like calculate that again, or is that just kind of not able to get it back anyway?
So for example, so this is from data that are available for us, right? So we can also extend the catalog to obtain other. So for example, if a survey has image in a specific patch of the sky, we can also always include this patch of the sky in the database, and it might be we might increase the data, but yeah. So I'm not sure if I answer your question.
Yeah, I guess I was just asking, like, is it possible to fill in the blanks in the data, like, or not, kind of thing?
Yes, as long as we might try to include the so for example, if you use a survey that has information around the full sky, and if there is a imaging paper that classifies some patch of the sky, we can cut out and cross match and do a visual inspection to increase the data available there. But we need some we always need ArcFinder are something to explore the data and including the database. Because if you, so for example, if you include only, so I know that the kids survey, a single tile is around 4 terabytes, I guess. I'm not sure I think the whole survey. So if you include the whole survey in the database, is very challenging. And so that's why we perform many cutouts, but these cutouts were basically related to the cross-matching with the data available in the literature. If not, maybe we need to run our finder, and then if there is a possibility to be a strong lens systems, then we can include the data, fill the gaps. So just to finish, just to complete my answer, let me go to a specific slide. Okay, I think. Sorry, my computer frozen. So we want to include the data. So for example, we want to include data from Delve. And at that time, the data wasn't available to the public, at least the cutouts. I'm not sure if it's available now. I think it is, but we can include the data from Delve and Hyperspam Chem Legacy Archive. And yeah, but we need to see in this huge imaging surveys to increase the data and redo it again, because there are a lot of data, especially from the South Hemisphere, that it is a catalog, but we haven't included in the database because at the time we didn't search for the cutouts. And this definitely will increase the data, because we know that there are many licensed systems that are already there, which was cataloged by other survey. We don't have the image available right now, but I'm sure that that is in the footprint of this survey.
So
And
we are already
yes, sorry.
time for the
Thank
questions.
you.
But okay, so
Thanks.
any very short question? I think you're already on time. But okay, so let's also record it. Renan will do a hands-on also on Friday, yes?
Yes, on Thursday.
Thursday, on Thursday. So sorry, so it will be on Thursday. So okay. So thank you, Renan. That's
Thank
it.
you.
So and now who's well, but here I have the title, not the persons, not the names. Check if it's passing. Okay. Okay. So now João Paulo França is going to present tagging and modeling a compilation of a strong lens system with the ground-based images. So you have 15 minutes plus 5.
Thanks, Davi. Yeah, so thanks for the introduction. I would like to thanks for the opportunity to give this talk. Oops, let me see if okay. So thanks to Hannah, I will skip entirely the introduction on the sample, and I will go straight to the classifications that we want to do with the Lasberu data. So I just want to highlight the motivations to do this compilation. So essentially one of our main goals with the Lasberu was to use it for follow-ups. So, and this is already a project that that we have already applied this data for in 2022. Other thing that I just want to highlight is we want to use all of the sample to make also to use for lookup tables. So for example, if a broker we get an alert of a transient, we want to cross-match this alert with the Lasberu objects and see if there is any hint of a strongly lensed object. But I think the key point is that since as Hannah already mentioned, our main goals with the Last-Beru database was essentially to use it in machine learning applications. So that's why we want to classify all of the objects, and with the best systems on this compilation, we also want to make the modeling I'll be showing in a few slides. But okay. Okay, so this is essentially the strategy to make the classifications of these objects. We intend to make the classifications based on at least two stages. The first one is what we call the vetting, and the second one is what we call tagging. So in the first stage, we essentially classify the nature of the object. So if it's there is, for example, any clearly visible arc or multiple images in an object, or I mean, if there is any sign of lensing in a particular object, this is very common from ground-based data. And with the best systems that will be classified in the vetting, I mean, for essentially these two options, definitely is a strong lens system and worth continuing for the tagging. So with the systems that will be classifying as these two options, we'll be tagging multiple properties for the lens, for the source, and also for the environment. So that's essentially the idea. So I just want to emphasize also that this classification is a survey independent classification. So for example, we'll be classifying the same object across different surveys. I think this is important, especially to test machine learning. I mean, to apply this data to machine learning, especially to check the domain adaptation of these applications from each survey and so on. So, okay, so speaking more about the vetting, there is only one simple question: which description represents better the object in the image? And we have 4 options. Definitely is a strong lens system. So I mean, you choose this option when you bet your salary on this system being a strongly lensed. We have the worth continuing. I mean, these are for the systems that you are not 100% sure, but there is a strong hint of being a strong lensed. Might be a lens. So for example, there is a central galaxy with a blue spot. So, well, might be a lens, but it can be used for it's not very interesting for some of the applications. So for example, for the modeling, so you choose the might be a lens option and no sign of lensing. So there is no sign of lensing in the object. So in the vetting, the user is going, I mean, this is the kind of image that the user see, just a smaller cutout of 20 arc seconds square. And on the tagging that I'll be showing in a moment, the user classified not only this smaller cutout, but also a larger cutout. This is important to classify the environment on which these lenses are. Okay, so we have already finished the vetting of these smaller surveys, and we plan to, you know, I mean, this is to have a collaboration of people from the LSSC, and many of you have already volunteered for the vetting. But just to give you some examples of definitely systems that were already vetted. So as I was saying, we have already finished the vetting of the smaller surveys. These are some of the examples of the best systems in our sample. So these are examples of might be a lens object. So as I said, there is a central galaxy, a blue spot, but well, we can extract much information on some of these objects. So we choose this option. And the no sign of lensing object. So there is not a central galaxy or any particular interesting aspect on the object. I mean, the plan is to, as I said, when a user choose definitely and worth continuing, is take the idea is to take one object for the vetting to the tagging later. But for these 2 options, I mean, we don't want to discard the systems that have been classified at might be a lens and no sign of lensing, but they won't be on the tagging. So for the tagging, the user see, as I said, a smaller cutout and a larger cutout, and the idea is to classify different properties of a strong lens system. So we'll be classifying if it's whether an extended arcs or if it's a point strongly lensed point source, strongly lensed object, a multiplied image. We also want to classify the lens, if it's an early type galaxy, I mean a massive elliptical galaxy, or if it's a spiral galaxies, as we saw yesterday. We want to classify the source, if it's a blue source, a red source. We also want to classify the arcs, if there is any contamination on the arcs. This is important for the modeling. We want to classify the environment, and finally, the imaging quality. So if there is any dead pixels or artifacts on the image, we also want to keep track on this. So this is the interface that the user see, and we are trying to document as much as possible, so the user can click on this button and see more information on each of the questions and in each of the options. The options have some examples, so the idea is to have a user-friendly classification. So this project is currently available on this universe. I'll be sharing these slides with everyone who is interested in our also in our Slack channel. So you can follow this link and see the page. This is the home page of the project. It's currently on this universe. Okay, so I will give you more details on the classifications on Thursday, as I will also have a hands-on. Okay, so speaking on the modeling. So just to give you a pictorial view on how the modeling works. For example, I'll be talking about what they call point source modeling. This is a technique that was essentially used in the early 2000s. So the idea is to use these bright pixels in each of the multiple images. And by assuming a mass distribution, you can also assume a shear component, which maps the weak lensing effect along the line of sight. But basically, assuming a mass distribution, which I show us this K in here, we can compare the brightest pixels with the predictions from the modeling. So we can solve the lens equation, assuming a mass profile and so on, and compare the observed peaks, brightest pixels, and the predictions from the modeling. So this is a simple way to do the modeling. But as I said, this is a technique that was implemented used in the early 2000s. But the downside of this technique is that you are losing a lot of information on the image. So essentially, each of these pixels carries out information on the mass distribution from which it was deflected from a foreground object. So what we do to increase the complexity and have better constraints on the mass distribution is to assume extended source. So this is an example of a light profile that we can assume to describe the lens and also the source. This is an example of a multi-Gaussian expansion light profile, which is essentially an expansion of individual Gaussian profiles. This is one example, a comparison between a power law that we usually use in the post-Newtonian parameter applications, and in comparison with these slightly more complex light profile. These are the residuals. The residuals are way better in the lens region. But this works fine for the lens, but usually in the source we have a highly, it's very common to have a highly complex shape of galaxy. We can have a strongly lensed merged galaxy, as I show here. This is essentially a simulation, but these are the arcs of a strongly lensed merged galaxy. And for this situation, the parametric light profile is not a good approach. So what we do is to consider Voronoi adaptive pixelization of the source plane. So the idea is to map the imaging plane pixels into source plane pixels, assuming a complex mesh grid of Voronoi. So these are some of the examples of source reconstructions. I mean, by using this technique and we've already the preliminary analysis on the vetting that we made on these Mahler surveys, and also as a result of previous selections for previous follow-ups, we have already selected some of the best systems in the Lesberu sample. These are some of the data. So for example, in the first column, we have the data, and on the second column, I have the modeling that we obtained with the technique that I just showed. So we have already modeled a sample of 150 lenses. This is already one of the largest sample in literature, which is quite nice to have. And I mean, we tested this this modeling technique in different surveys, and I mean, it seems to work fine. The idea is to feed back the Lesberu sample, not only with the classifications, but also with these modelings and also the modeling products. So masks, segmentations, source reconstructions, and everything. I mean, these products. So just to give you an idea on the source reconstructions on some of these objects. I mean, for the same objects. So okay, so just to briefly give you an introduction, an idea on the applications that we can make with this modeling, with the Lesberu sample, and so on. So Ingrid already mentioned it in her talk yesterday, but so these are the 21 strongly lensed systems that were observed. I mean, we've made the follow-up in SOAR in 2022. This is the spectra that she analyzed, the final spectras. And I mean, with these final spectras, we can extract the velocity dispersions. This is especially important for testing modified gravity and inferring the sleep parameter. I just will skip. So yesterday we saw the modified gravity test. So for example, we is extracting the velocity dispersions from the spectra and also inferring, modeling a velocity dispersion, and also using the information on the image modeling, which is encoded in, it's encoded on this parameter, the Einstein radii. We can compare these two quantities and set constraints on GR because we have a dependence on this leap parameter here. So by comparing these two things, we set constraints on the post-Newtonian parameter, which this result in here. And here on the right-hand side, we have a comparison between our sleep parameter, the sleep parameter that we inferred on this data, and in comparison with other works in literature. I mean, there are a lot of interesting aspects on this inference. I think the most important one is that this is one of the first constraints on this sleep parameter from the ground. I mean, fully from the ground-based observations, not only on the spectra, I mean, the follow-up, but also modeling ground-based imaging data. So, okay, so I mean, we know that many of the authors of the follow-up proposal, it's currently on the audience. So I just want to mention that we decided to break this analysis on two papers. And I just want to mention that these two papers are on a final stage of writing. So we'll be contacting all of the authors soon. This is the name of the paper. So joint arc samples for investigation into relativity, follow-up observations and implications. Já foi. So yeah, this is a Martin's idea. So okay, so just to briefly summarize, we have the sample that Renan showed to us. The idea is to start the vetting and tagging campaign soon, especially for the other surveys, for the larger surveys. The idea is to model the best objects on the survey using the technique that I showed. And I mean, the idea is to use all of these complex database to the applications. I mean, the follow-up observations that, as an example of what we already made, and also use this data for setting modified gravity constraints, for example, and also your project, the particular project that you are interested in. So yeah, I think I'll finish here, and I'll be happy to take questions. Thanks.
So thank you, João. Questions? Yeah.
Hello, João. Great talk. I want to know if the 150 systems that you modeled, you use all the systems you use the Voronoi cells method, or you use the parametric approach either?
Yeah, for all of them, I use the Voronoi source reconstruction. I mean, on this panel, I just show 100 of them, but I mean, for all of them, I use the Voronoi source reconstruction.
Okay, so actually we are on time also for the next talk. So let's thank again, João.
Thank you.
And now it's a talk of Victor Ramos. Victor, yeah.
Hi, everyone.
So now, Victor, so.
Thank you. Hi, everyone. My name is Vitor. I am a master's student here at CBPF. And I'll be talking about the work that I'm developing for my dissertation. I'm working with Professor Clécio Dibon, and we are developing a fast and automated method to model strong lensing images using wide field images. So I won't explain strong lensing to you. I'm sure all of you know probably a lot better than I do. But I think it's important to highlight here that strong lensing data from real systems is very useful for a lot of things that we can do in physics. We can use it to probe mass distribution in galaxies, which in turn can give us a window into dark matter physics. We can use it to make measurements of the Hubble constant, which is a big problem in cosmology today. The magnification effect that strong lensing causes can be used to study high redshift objects, and we can use data from these systems to find constraints on models of modified gravity. So there are a lot of applications to real data of strong lensing, and it's really important that we find a way to extract that information so we can use it to do new science. It's not working. Okay. So okay. Again, I'm sure many of you know that we don't have a lot of strong lensing systems that are already observed and modeled. But there is a big expectation that surveys in the future, like LSST, will greatly increase the number of strong lensing systems that we observed. So, okay. So, I'm sorry. There's an expectation of a big increase in the number of strong lensing systems that we have observed for the next few years. So for the amount of data that we have today, the volume of data that we have today, the methods that we use to model that data they're fine, they work fine because we don't have a lot. And having methods that are not automated or that take, I don't know, a few hours, or maybe for a more complex system, maybe a couple of days, that's fine. But we could be expecting hundreds, maybe even thousands of strong lensing systems, detecting hundreds or thousands of strong lensing systems in a single day. So we do need some way to go through this data very quickly. And there has been some success doing this with neural networks in the past. Most of these methods used convolutional neural networks, which offer really good inference values, but they have a limitation when it comes to uncertainty estimation. And so that we can, for us to do proper uncertainty estimation, we usually want to work under a Bayesian framework. So in order to do this, we're going to be doing using a method known as simulation-based inference. So to understand simulation-based inference, we need to think of this problem under Bayes' theorem. We want to infer, we want to find the probability distribution of a parameter given an image, in that case, probability of A given B. And we know that this is given to us by a product of the likelihood, the probability of an image given a parameter, and the probability distribution of that parameter, the prior distribution. So for this situation, the likelihood is usually not tractable. We can expect to have an analytic form for the likelihood. So we need a method that does not depend on a likelihood distribution. And simulation-based inference suggests that we use a simulator that acts like this likelihood distribution. Essentially, we feed it a parameter A, and it gives us an image of a strong lensing system with that parameter B, but this simulator needs to be stochastic in some way so that it acts like a likelihood distribution. And then we can reconstruct our posterior distribution using a prior distribution on the parameter and this new simulator that replaces the likelihood. And to do that, to relate the posterior distribution, which is what we want, with the other distributions, we use some sort of neural network-based density estimator. In our case, we chose to use normalizing flows, but there are other methods. If you're here on Thursday, I will explain a little bit more about how normalizing flows work. And well, the idea right here, for now, what you need to know is that a trained normalizing flow is able to be shown an image. You show an image to this model, and it gives you a measurement. It essentially takes a sample from the posterior distribution, once it's trained, of course. And then if you show the same image many times to this model, it gives you the distribution of that. Well, you get that posterior distribution in a frequentist approach. Well, for this, we do need a simulator, of course, and for our application, we're using deep lenstronomy. It's an interesting package because it's capable of generating somewhat realistic strong lensing images, and it gives us presets of real surveys. In our case, we're using the preset for the Delve survey, which gives us realistic PSF and noise parameters. And to feed the parameters, the strong lensing parameters to the simulator, we're using LensPop to generate a big population of DCAM observable lenses. So we take the population that LensPop generates, we feed those parameters into deep lenstronomy, and we get this data set of about 25,000 images in 4 bands of Galaxy strong lensing. So before showing these images to our model, we take a step of image preparation. We do background removal and normalization. And before instead of actively showing the images to the density estimator, we use an embedding net, which is essentially a CNN that summarizes the information in an image into a smaller vector, so that the density estimator works with low dimensional data and it can be trained much faster. For this, we're using an inception architecture, which is a well-known convolutional neural network architecture. And for the density estimator, the architecture of normalizing flow that we're using is named neurospline flow. So an important parameter here, we're trying to infer 4 parameters of strong lensing. The Einstein radius, the velocity dispersion of the lens galaxy, and the redshifts of both the lens and the source. And we're using separate models for each of these parameters. We don't train one single network to do all four. That gives us a lot more flexibility with the architecture and hyperparameters of each model so that we can get better results. So far, these are the results that we're getting. On the top left, we have the Einstein radius. On the top right, the velocity dispersion of the lens galaxy. On the bottom left, the redshift of the lens, and bottom right, redshift of the source. What you're seeing here is a 1-by-1 plot. So on the x-axis, we have the true value, the value that was used to generate a simulation. And on the y-axis, you have what the model predicts for that value. So in blue, you have the 1 sigma confidence interval, and in green, I'm not sure if you can see this, but there are the 2 and 3 sigmas confidence intervals. What is very clear here is that regions of lower sample size, like redshifts above 0.4, for instance, on the lens redshift, they tend to give off much worse results, and this is, of course, because of the low training sample. There's an important caveat here. We recently found out that there is a slight issue with the way that the redshift of the source is being simulated. So the results on the right, both the velocity dispersion and the source redshift, just take them with a grain of salt. They're here to show that they can be done, but they're not necessarily being done in a realistic way right now. So to analyze these models, we have a few metrics that we can use. We have the median precision. All models have achieved values between 70 and 85%. We have also the median fractional deviation, all below or close to 10%. And we have the correlation values for those 1-by-1 plots, the Pearson values. An important point of using simulation-based inference is analyzing whether your posterior distributions are reliable. I won't go into a lot of detail on these two metrics here, but I can talk about them more on the hands-on session on Thursday. But generally, what we want is a model that does not offer posteriors that are either overconfident or underconfident. We want the posterior width to be just right. And we can test whether our posteriors are their width is a proper value by analyzing how many in a test set, how many of the true values are covered in a certain percentage. So starting from the center of our distribution, if we analyze the 20%, so from the 40th percentile to the 60th percentile, how many of our true values are covered? And we usually want that to be 1-to-1. So at 20%, we want 20% of the values. At 50%, we want 50% of the values. And what we can see here is that all the 4 models are well calibrated. The model for the Einstein radius is very well calibrated, but there are some slight over and under confidences, but generally the models work well. There are no signs of systematic over or under approximations of our posterior distributions. So we have offered a fast and automated method for strong lensing parameter inference. We're working with about 2 minutes for 2,500 lenses. This is pretty fast. I hope it's fast enough for LSST. We've shown that the models are both precise and accurate to some extent, and we have taken steps to ensure that the uncertainties that we're reporting are reliable. Currently, we're focusing on adapting these models to work well on real images, which has been a challenge. We're using some images from Delve survey and now some of the images from the LessBeru database. And to do that, we're exploring different architectures and different preparations of the images. So thank you for watching.
So thank you, Victor. Questions? Yeah, Martin.
So I have two. Okay, I have two basic questions. So, but if you think they take too long to reply, maybe we can move this to the discussions. So one is that in your, I mean, your ground truth values are numbers, like the Einstein radius, but the output of your network is like a PDF, right?
Exactly.
So what is your loss? How do you build the loss for training this sample?
This is kind of complicated because the loss is measured on the normalizing flow. It doesn't work like a regular neural network. It uses neural networks to define parameters for a transformation on a basic probability distribution. So the loss for this is hard to explain. It's essentially a log probability of that distribution. The actual loss value is the negative of that because we want to minimize that, but it's the log probability that the point that your neural network generated has come from the distribution. The inverse of that, once you show that image, it grows through the network and it comes out a single value. Okay, and that single value is compared to the right value. This is what is happening. The PDF is generated in an after step. So it's generated by showing that same image many times to the network and building that. So it is based on the log probability that that point that the network outputs is taken from the probability distribution that you're trying to model.
Thank you. So the second question, well, maybe if, yeah. The second question, I think it's in your slide, but maybe I didn't understand. So when you plot like in the 4 quantities that you recover, so there you are comparing like the mode of the like each point there is the mode of the distribution of the value that you recover.
The median.
Right? Or the mean. Okay,
median,
the
yeah.
mean. So, okay, so, but this doesn't tell us how well your error bars are being computed.
Well, the error bars are the intervals here.
But this is like the error bars even if your data points didn't have error bars, you would have this shaded region, right? Because you're having lots of systems.
So, no. In this plot specifically, I'm binning the data. So this region, the blue region here, is the average. I take samples from. I get the median and the 1 sigma, 2 sigma, and 3 sigma values for each point. So in this bin, I'll have, let's say, 100 points, and I'll have 100 medians, 100 1 sigma, 100 2 sigma, and 100 3 sigma values. So I'll take the average of each of these, and this is how I build this plot specifically.
Okay. Thanks. Yeah.
Just a moment.
Unless it changed the code, because this plot was originally a code that I built. So I don't know if you changed this. The blue one is actually the statistical region you are asking for. And then the green ones is what he was saying. I don't know. Did you change it?
I changed it.
Okay, so it's not anymore. Okay, but it used to be. So I used to compute the statistical standard deviation and 1, 2, and 3 sigma from the distribution itself. The average 1, 2, and 3 sigma. So it's not anymore, but it can be plotted.
So can you explain the next plot then?
What do you mean next plot?
So the following plot after that?
This one?
Yes.
It's a measurement of how reliable your posterior is. So what we do is once you have a test set, let's say 2,000 images, you generate a posterior for each of these 2,000 images. So for simplicity's sake, let's imagine they're all Gaussian. There's a median and there's a spread. What we are doing here is that for each confidence interval, so as we as we analyze our posterior coming out of the center and increasing this interval, how many times is the true value of that parameter covered in that range? So for 20%, as I said, from the 40th percentile to the 60th percentile, does that cover, we test for each one of the 2000 images, this is the true value within that range? And if it is, then we consider that the empirical coverage, that is part of the empirical coverage. So as we increase this interval, we expect the empirical coverage to increase linearly. And that's kind of what we're getting here. We have a good, very good empirical coverage for the Einstein radius, but it's not so good for the other parameters. Still, at the rate that this is right now, it's not a cause for concern. The uncertainties are still well calibrated.
Thank you. Very nice work.
Okay, so more questions. So let's thank Vitor again.
Thank you.
So now we have a discussion with all the talks. So Renan, are you online as well? I don't know if is it possible to see who is online? Yeah. Sure. Not online. Okay. Okay, but so we have Vitor and João. Sorry. Yeah. I cannot see it. Okay, now I can. Okay. So okay. So Cristina, what?
Hello, everyone. I have a question to Vitor. Very nice work. I was wondering how much the results depend on the simulation you use to train or to calibrate, because the simulation doesn't seem very realistic in the sense that you don't have any other objects in the images or any other artifacts that we have to deal when we use real observations. So I was wondering how you plan to work when using real observation. Are you planning to mask everything around the arcs, or plan to create more realistic simulations?
Well, to answer your first question, they are extremely dependent on the realism of the simulation, as we're figuring out. The results in real data aren't that good with these simulations, exactly because they're not that realistic. My plan is to use real images of galaxies and simulate only the arcs, which should give us much more realistic results. But this is honestly the biggest part of the work so far, figuring out how to have realistic simulations, at least realistic enough to give me good results in real data. And this is what the challenge is being so far.
Thank you.
Carlos. Okay. So Carlos, you may go ahead.
Hi everyone, hope you can hear me. Very nice talk, Vitor. I have a question just to see if I understand correctly. You say that you have one model, one neural network, or something like that for each of the parameters, right?
Yes.
So since we have one for each of the parameters, we don't have any covariance in recovering these quantities, right?
Yeah, exactly.
Oh, no, sure. Just to make sure. Thanks. That's really nice.
Yeah, they work as completely separate models. I have four completely separate models that do completely different things. One measures the Einstein radius and the other measures the redshifts, and they have no connection whatsoever.
Yeah, that's really good because, yeah, my question would be like, if you have information from the redshifts, if this may improve your modeling, but since they are completely independent, that doesn't make any difference, have additional information.
Well,
so, yeah.
their results don't affect each other, but for instance, the modeling of the velocity dispersion depends, it works by assuming the SIE model and for the mass distribution. So, because this is what we're using in the simulations. So it essentially works by measuring distances of lens and source galaxies, measuring the Einstein radius, and then inferring that the velocity dispersion. So the neural network is within itself at some point measuring those values, but it is trained. The training process aims to find the velocity dispersion value alone. I don't give it any information about redshift. The neural network learns whatever it needs to learn to get to the velocity dispersion, and that might include other variables such as the redshifts and the Einstein radius.
So it's possible if you have this information about the redshifts to improve your measurements about the velocity dispersion, for instance?
Yes, it is possible, but I don't know. It seems that if the goal is to use this for a big number of lenses, we're not going to have that information. So we want something that works just with the images. We just something very independent.
Yeah, no, I see. I'm just thinking about applications of this because I'm kind of old-fashioned way in modeling, so I prefer this parametric modeling. But I think that using CNNs and this kind of stuff to build good priors is a good thing to do, because you usually have to assume broader priors in lens modeling, which makes the overall modeling very time-consuming. But if you can use these NNs or any kind of this to build better priors, and like you spend 2 minutes to modeling all the systems. So I think that using this to build priors is really quickly. So this can be very useful to people like that want to do parametric modeling as well. So
Yes.
yeah, thank you.
Martin has a question, so.
Yeah, I have a question, a comment. The comment is general. Renan had to leave, but if you have questions, well, we can either ask them here, so I may answer them, or you can type them on Slack. So Renan is available to reply to questions. And the same for Ingrid. In her case, it's less likely that I should be able to reply, but you can try. And also, she said she's available to reply to the questions in Slack. And that holds for everyone. Some people are not able to be present when we are broadcasting the talks, or they have to leave. So just feel free to pin, to write to them in Slack, or to pin their advisors. Okay, so the question now. I mean, the question is what is basically what Carlos just asked is about the correlation of the variables, right? Because in your case, like theta Einstein, sigma v, z lens, z source, they are correlated. I mean, if I know 3 of them, I know the 4th. So can you train a network to try to infer simultaneously, let's say, these 4 things, but computing like covariance matrices, not only individual PDFs?
Yes, we can. That was our first approach, training a single network. But it ends up being a problem with computing power. We would need a network with a lot of parameters, a very complicated network that would take a long time to train, that would be super sensitive to hyperparameters to get good results for all 4 parameters at the same time. So having different networks for each parameter allows us to use slightly different architectures and hyperparameters for each parameter of the lens that we're trying to infer. So that gives us a lot more flexibility doing this. It's mostly heuristic. We tried that and it works better like this.
Hi, just a couple of comments. First on the Christina's question. So there is a big leap between going to the simulated images and the real image. That's a big challenge. I wouldn't say the most important thing is more objects in the field. Yes, this is important. But we end up seeing how sensible we are with the contrast variations, how the counts are defined. And this is pretty tricky because we are not using our own simulation codes. So sometimes we don't really understand how these things were defined in terms of observations, right? So that's a very tricky part. I expect to solve this issue in terms of the next strong lensing challenge we are preparing inside Rubbing, because we are dealing exactly with the person who did the code, right? And they're expected to have crowded fields too. So many objects, stars, and so ever. But I wouldn't say that the many objects in the field are the biggest issue. I would say how the observation is defined and the details, these are kind of tricky. And also because we decided to do the hardest way. Most of the papers that make this kind of modeling, they subtract the lens galaxy, right? We could do that, but we think would be more interesting if we could even get this information before making the subtractions, because we know subtractions take time, and also because subtraction can leave artifacts, right? So many people that tried this kind of approach did this in HST images, in so high resolution image, and making subtractions. As far as I was following this literature. So I would say that's for your comment. And I think doing the answering Martin, I think making a single neural network, that definitely is the best choice in terms of reliability, right? People would believe the results, because otherwise you can get a very poor redshift with a poor velocity dispersion. Who would believe that, right? So that's one of the things. We did try this, as Vitor said in the beginning, but I think the deal breaker of that part was understanding the image. I would say that if we start from now, we could try it again if you want to, and maybe this will end up being a different story right now. And also, the computing power at that time was different also. So we are talking about 2 years ago, around 2 years ago. So things have changed. So I think it would be nice to have this try. But Vitor is the end of his master right now. But definitely something we should try, if not for continuation of Vitor's work, at least for the next strong lensing challenge, if it includes the modeling part, which I expect it to include, right? So that will be my comments.
So
So just a comment that before lunch, we have more time to discuss this topic, both on the last Beru and both on the machine learning side, so we can continue those discussions.
so yeah, so now it's coffee break. So it will be, but it will be, I forget to see 15 minutes. I forgot to see before. 20 minutos. Okay, so in 20 minutes we get back. So see you soon.
mass X-ray luminosity relation
Boa tarde, bom dia ainda, né? A segunda sessão é porque, para quem tem filho pequeno, a gente acorda de madrugada, então eu já não sei o que é bom dia, boa tarde. Mas enfim, então a gente vai começar a segunda parte da manhã agora do nosso evento, e a gente tem hoje agora a apresentação da Isabel Pederneiras. Ela vai falar sobre the evolution of the MLL relation in the Codex Galaxy Cluster Sample. Ela fez uma gravação, ela fez um talk pre-recorded, o Martim vai dar play aqui pra gente. Eu estava querendo verificar se ela estava online, mas eu acho que ela não está. Isabel, se você estiver aí, você avisa aqui pra gente, tá bom? Martim, pode dar. Ah, ela tá?
Good morning, everyone.
Tá.
I'm Isabel, and I'm very pleased to be presenting a bit about my work, which is the evolution of the mass X-ray luminosity relation in galaxy clusters using the Codex catalog. So I'll start with a brief introduction, then I'll talk a bit about the galaxy cluster sample we used, following by the statistical analysis we developed in this work, and in the end, I'll discuss our main results. So, galaxy clusters. We know that the first structures to form were small structures, and then they merged together to form the larger structures we observe today. And in this scenario, the galaxy clusters, they occupy this unique position as being the most massive systems that have already reached a certain degree of dynamic maturity. And indeed, they are very massive. Their masses can go from a few times 10 to the 13 solar masses, which we call the group regime, and can go up to a few times 10 to the 15 solar masses. And due to these characteristics, the clusters, they are kind of on this intersection between cosmology and astrophysics. For example, they are the object of studies trying to constrain dark matter properties or to better understand the physics of the gas of the intercluster medium. So I'm going to talk a little bit more about this intercluster medium because it's a very important component of the cluster. So if we consider the entire mass of the cluster, around 3% are thought to be in stars in the galaxies, and about five times this amount are actually on this gas of the intercluster medium. And of course, the majority is dark matter. And so this intercluster medium is actually this hot plasma composed mainly by hydrogen and helium ions and free electrons. And this gas is actually an ideal environment for the X-ray emission by what we call thermal brainstalling radiation or free radiation. And indeed, we observe these structures as being very strong X-ray emitters. And here I'm showing an image from the Hubble telescope on the optical, where we can see the galaxies of the cluster overlapped by another X-ray image from the Chandra telescope, so such that we can see this strong X-ray emission here. And with that being said, what is the importance of studying scaling relations, right? Well, we know that it's very important to quantify the total mass of the clusters, because the number density of clusters as a function of their masses are actually very sensible to some cosmological parameters, like the mass density and sigma 8. But the methods that we consider more direct to measure the masses of those clusters, for example, with gravitational lensing, are thought to be more expensive observationally. For example, they usually need high-resolution images and precise estimates for redshift, right, for the distance. And that's kind of difficult to do for a large sample of galaxy clusters. And that's why it's so important to calibrate scaling relations, because then we can relate the entire mass of the cluster with a more accessible observable. for example, the X-ray luminosity. And what's the form of these scaling relations, right? We usually use purely gravitational models. Here I put the self-similar model, which predicts a power law relation between the X-ray luminosity and the total mass, with an exponent here equal to 4/3, which is roughly 1.3. And here we're talking about power law, so we can use the log of this relation, and then we can work simply with a linear relation. So that exponent will be actually this slope, beta, and we also want to analyze if this relation can evolve with time. So we also introduce a new term given here by 1 plus the redshift, and a new parameter gamma, which is our evolution parameter. So what we would expect from theory of 4/3, and we wouldn't expect any temporal evolution. So the gamma parameter would be 0. But like I said before, this is a purely gravitational model, so it doesn't account for AGN feedback, radiative cooling, or other phenomena that can cause some turbulation in the intercluster medium. And we know that those phenomena are present in galaxy clusters. We observe them, so we might expect some deviations from these predicted values. And that's exactly what we want to confirm, right? We want to calibrate this relation and confirm the values. So what's the cluster sample we're going to work with? Well, we work with the Codex catalog. Codex here stands for Constrained Dark Energy X-ray, and it's basically a reanalysis of the Rosat All-Sky survey in the area of the Sloan Digital Sky survey. So we have our first detection of the source in the X-ray images from Rosat, and then they use the red mapper algorithm with Sloan data, which is in optical, to make this double identification. So they are identified both in X-ray and in the optical. And as for our subsample, we chose those clusters that had mass estimates by weak gravitational lensing, not only because this method is considered less biased, but also because it's independent of the X-ray luminosity, which is good for our case since we are trying to analyze the mass X-ray luminosity relation. So we use 3 different previously published catalogs. The first one is from Kivari et al. From 2021. They used a subsample of Codex clusters for follow-up observations with the Canadian France-Hawaiian Telescope, CFHT. And we use all of these samples, all of these clusters. We also use the work done by Urbonnet et al. From 2020, where they made the weak lensing analysis for hundreds of clusters with observations with CFHT as well. And we use 46 of these clusters in our analysis. And we also use the work done by Oguri et al. From 2021, that they also made the weak lensing analysis for hundreds of clusters in the Subaru program. And from those, we use only 27 galaxy clusters that were also present in the Codex catalog. And here I'm going to highlight the first subsample from Kivari et al. Because we were granted access to the entire pipeline they used for the weak lensing analysis, such that we were able to retrieve the entire mass PDFs. So I'm just briefly gonna show what they did. They used a lens fit algorithm for measuring the shape of the source galaxies. They also used 2 photometric redshifts catalogs to estimate the distances, and they assume a Navarro-Franken-White density profile. And with these assumptions, they were able to estimate the probability of measuring a superficial density profile delta sigma, given that your cluster presented a true mass M. And they assumed a normal distribution given here by this equation. And what's interesting in here is that they define a covariance matrix that accounts for pretty much every uncertainty that might arise when you're trying to do a weak lensing analysis. For example, the intrinsic ellipticity of the source galaxies, or the triaxiality of the cluster halo, or for example, the errors when trying to define the center of your cluster, among many other uncertainties. So all of this is accounted in this covariance matrix. And we use this probability as our mass PDFs for these subsamples. And here in the right, I show an example for one of our clusters. Here we are working in the logarithmic space. So the Gaussian is actually kind of tilt, okay? So to sum it up, here we have all of our samples in the X-ray luminosity and mass plane in the left figure. And we can see that most of our clusters, all of our clusters really, they are high mass systems. All of them present a mass over 10 to the 14th solar masses. And on the right here, I'm just showing a TOF projection of our samples and the Codex catalog. So we have our cluster samples, and we have the linear relation that we want to calibrate. But then you might think that it's enough to just do a simple linear fit. And to be honest, that's what most works do. They use a simple linear fit, but that's not what we wanted to do in this work. We wanted to create a more robust statistical analysis to account for biases and selection effects. And here I'm just trying to illustrate a bit why this is very important to consider. So in this graph on the right, I have the log luminosity and log mass plane. And here I have a straight red line that represents this true scaling relation that we want to retrieve. So we can see that the data is not exactly over this line. It presents a certain intrinsic scatter. But even though we have this intrinsic scatter, this is not a very realistic scenario, because what we have on our universe is that we can see much more low mass systems than high mass systems. It's what we call the halo mass function. So this here is actually what would be a more realistic scenario. And also when we are trying to construct a survey, we also have a flux threshold where below this threshold, we simply cannot detect the source. So what we have would be something like this. And after that, we also do many selections. For example, what we actually consider a cluster, or perhaps if I want to work with a more pure sample, I'll make some cuts. For example, I just want to work with clusters that has over 100 galaxies. So you're gonna make some cuts, usually more than one cut, more than one selection. And of course, in the end, you also have measurement errors, right? That will depend on the instrument you used and the method that you use for estimating the luminosity and the mass. And if you just make a simple linear fit without considering all those effects, you end up having a result that is not meaningful, right? It's not the result you wanted. Because in the end, you're working with a sample that is no longer representative of that original population. So what we wanted to do in this work was to create a model to account for all these effects. So we used Bayesian statistics and we created our own Bayesian hierarchical model. Over here on the right, I'm just showing very briefly our likelihood function. And what I want to highlight here is this function here that accounts for the selection effects. And that's very important on our work because we have detailed information of all the selections made in constructing the codex catalog. So we can model these functions with precision, right? So very briefly here, I'm going to show a few of them. We consider the completeness both in Rosat data and Sloan data, so both in the X-ray and in the optical. We also created a function that basically tells us how much representative is our subsample of the entire codex catalog. And we also used another function, a simulation, that basically tells us the probability of detecting a cluster given its redshift, X-ray luminosity, and intrinsic scatter. So we made this entire model and we then apply it to our sample. And here is our main result. On the graph here on the right, I have the X-ray luminosity and mass plane. And the red line here actually represents the slope expected by self-similarity, by theory. And what we can see is that our results actually differs a lot from what was expected, right? We found a slope value much smaller than what was expected. And we also found evidence of positive temporal evolution. And we actually found those results unexpected, right? We didn't expect them. And so we made a lot of tests, many fits, to see the impact of each term of our statistical model and the entire statistical model as well in our analysis. And what we found was that for the slope value, this difference we found was most likely due to the sample we use, not the statistical approach we adopted. Most likely it's because these high mass clusters, for some reason, they behave differently, that we don't know exactly why. And as for the evolution parameter, we found that the most important factor was to consider the halo mass function. If we don't consider this function, we end up with an evolution parameter very close to 0, but with very large error bars. So this term, this halo mass function, was very important to constrain the evolution parameter. And well, that was it for today. Although this is a pre-recorded video, I'll be here online to answer any questions you want. Thank you very much.
Sorry, I was speaking Portuguese at the beginning. I didn't realize we have non-Portuguese speaking people in the audience. Can you put the sound down? Thank you. So another warning is that we are not, unfortunately, Caio Oliveira had some major personal issues, so he's not able to attend. That's one of the reasons we delayed the first presentation. We keep on schedule. Do you have any questions for Isabel? Comments? Please, Karin, I'll give you the microphone.
Hi, Isabel. Very nice work. I was wondering, the last plot that you showed, it wasn't clear to me the distinction. Basically, it seems that the most massive clusters, they're somewhat under luminous in the X-ray from what you expected. And but since there are no, you had shown error bars earlier on, but I don't know. I mean, it's pretty, there's a lot of scatter around that. So I was wondering if it's, if you have some guidance as to what could be, if it's really just that the most massive ones are under luminous, or if you have some other sources of error.
Isabel, did you hear the question?
Hi, hi, can you hear me?
Yes, it is
Oh,
loud, but we heard you.
sorry.
Don't worry.
I don't know how to manage that. Uh,
Okay, it's not your fault.
uh,
Probably something in our system here.
I'll talk like this, perhaps.
Perfect. Don't have
So,
to be-
yeah, yeah, we usually expect a larger scatter for high mass systems, for high mass clusters. Um, but it's very unexpected, our results. When we actually consider the group regime as well, we made a simple fit with it because the groups were not codex catalogs, so we couldn't use our whole model. But when we made a simple fit, we retrieved a result very similar to what was expected by self-similar theory. But when we consider only these high mass systems that we chose, the difference appears, this large difference, especially in the slope, right? So we don't know exactly what could be happening there. It might be because we simply selected some clusters that are not they are not relaxed, perhaps, but we don't know exactly the information of each cluster we have. We should look into this. And well, that's about it. I mean, there are a few studies that says that we should expect a higher inclination for the group regime and a shallower relation for the high mass regime, but not so low as we found. I mean, we found a it's very different. We found a very unexpected result. So yeah, there's a lot to be studied from this, I think.
Okay, so we have another question from Marty, but I hope it's a quick question because we are on time.
If there is no time, I can ask in the discussion session. But I think it's a short question. So very nice work. I guess the correction, well, all the corrections you made were important, of course, but I guess they are even more relevant when you have a small number of systems. So what's next now? Like, do you plan to do this maybe with eRosita clusters and then LSST or JPass images? What do you think is next for larger samples?
Hi. Yes. First, we want to use and do something similar with eRosita data, and we want to calculate ourselves the masses, right, from weak lensing analysis, because we used different works, and we couldn't account for many things when using the mass estimates. So we want to calculate ourselves probably with stacking analysis, but we calculate ourselves the mass from weak lensing with eRosita data. Yes, that's for my PhD. I'm trying to do this now.
Okay, so if you have more questions, let's save it for the discussion. And let's thank again Isabel.
Thank you.
So now we have Davi Rodrigues. So David, please.
Okay, so thank everyone. Thank for opportunity of the talk here. It has been very nice to talk with you in this. This is an informal, small meeting. It's very good to have different ideas. I'm going to talk here about a work that I started in Heidelberg. In the last year, I was doing previous year. I was in Heidelberg, where I started also to work with the gravitational waves. And it's related to this work here, this already published work, and this work here that we are in preparation with this Italian group here. So here we also, this one has Quartin that you know, that's Miguel Quartin. Here Kumar is an Indian that is in Germany. This is myself, and this is Luca Mendel from Germany as well. So the idea is, but by the way, this topic, as I told Miguel, sorry, to Martin, it is not, let's say, very close to gravitational length. It has some relation, but it's not that close. So, but it's okay. Well, let's talk about let's see about the relation between black holes and cosmology. I know that black holes are the most Kerr black holes are the most relevant solution for astrophysics, because we Kerr black holes are black holes that rotate. Okay, and these are asymptotically flat solution. That is, you consider in your space time, so that when you go far away from your black hole, you find just Minkowski. Well, asymptotically flat is a natural approximation for studying black holes, but the universe, we know that's not asymptotically flat. There are extensions of the Kerr black holes, the Kerr de-Sitter one, which this is a very simple one, in which you have a black hole in a de-Sitter universe. So you go far away, you have de-Sitter. This is also, let's say, quite simple case. But still we are dealing with black hole in vacuum in the sense that your energy momentum tensor is nothing. We only have a cosmological constant. The situation is more interesting when there is matter. When there is matter, the simplest case is the Mach-Witt solution. And the solution is not, let's say, is kind of polemic, some of its interpretations. In some sense, it's a very natural solution, because this is, if you put this m of t here as a constant, this would be exactly the Schwarzschild. Put this mt equal to a constant, and put this a here also to be 1. And then you find exactly Schwarzschild solution in isotropic coordinates. When you put m equal to 0, you find exactly Friedmann-Hobbs-Ock solution. And when both can vary, both m and a, you find something that interpolates both cases. So the extremum case is very well understood, but the interpolation case is not so simple. There is some discussion what exactly this thing here, but let's say it's a kind of black hole. The main point of the solution, that is the base of several other solutions in which we studied currently about black holes in cosmology. For instance, this discussion started when some people started to think about possible consequences of the universe expansion into local solutions. Actually, it's some people say simply that it's impossible for cosmology to have any impact on a local solution. Actually, this is wrong. This is easy to find that this is wrong. It's possible for cosmology to have impacts on local solutions. This is one of the several examples. This is the null solution. Null solution extension of you start with above matter with constant density. Which if you put it that far away, you have only Minkowski, you have what's called the interior Schwarzschild solution, which is above matter of constant density. It's not a black hole. It's not Schwarzschild solution, it's another thing. I just have above matter. But then you can extend this to put in a cosmological setting, and you find a null solution. Null solution have above matter of constant density, which is not accreting, but it is enlarging. It's enlarged itself due to cosmology. This is not modified gravity. This is just GR. It is a well-known solution. A well-known, I mean, well known for for people that study this kind of solution with spherical symmetry. It's a kind of interesting because you have, as I said, you have the radius is co-moving with the cosmology. So you have a clear thing that you have very compact objects, clear compact object, which is influenced by cosmology. Okay. We can, but this is just one solution. There are several solutions within GR. I'm not going away from GR. This is the Sultana Deer diagram. I don't know how to say. Then they consider the possibility of a accreting black hole, and also then you see that we'll have some change of mass. In this case, there will be accretion. Also, you change the radius. That is, there's an interaction between the black hole and the background. Okay, actually, this solution that I present to you, they are quite old. For instance, the McVitie solution from 1933. So it's not that recent ones. But this kind of cosmological coupled black holes became famous more recently, particularly last year, due to especially two papers, one in Astrophysical Journal and the other one in Astrophysical Journal Letters, which show that the first one is more observational, show that they find that the black holes increase their mass, the supermassive black holes increase their mass in a way that no one know how to explain it. And the second one, it has also a theoretical side in which they model for this increase of mass, and then find that this mass is compatible. It's a radical increase of mass, actually, because the mass increases proportional to the scale factor, cosmological scale factor, to the power of 3. So if it was proportional to A to 0.1, for instance, that would be already interesting because you will have that the mass of the black holes will be increased correlated with cosmology. That would be already interesting. But they say that's proportional to A to the power of 3. That's quite radical. And they say that K equal to 0 is ruled out as high significance, I think, about 3 sigma. High sigma, okay. And okay. And this, so this is okay. It's here. Okay. So the standard case, K equal to 0 is rejected at a high level and favor K equal to 3, actually higher than 3 sigma. Okay. So and this paper actually they do something interesting. They put together two quite radical theories and find some interesting results. First of them, that black holes would increase their mass correlated to cosmology. These are a type of these cosmological black holes. The other one is this theory of geodis. I forget now the name. It's this geometric. No, not geometric. Sorry. Okay, this is not this geodis. I forget its letter here, but it's a proposal in which you have the dark energy could be sourced by local structures. So instead of dark energy be homogeneous distributed, it could be sourced by local structures. Something like black holes, for instance. And this is possible to have something that's closer to what you understand as dark energy if these things, these geodes, they increase their mass, increase cosmologically proportional to A to the power of K, with K equal to 3. So the idea actually is quite simple. It's quite intuitive in this case. You have something that you know that the energy density of a dark energy should be about constant. The energy density of dark energy does not change. But these things here, what's happened? They are their density. You know that dust decreases inverse of A to the 3. So these things here, they increase their mass proportional to A to the 3. So the point is that you have, in the end, you have this cancel out, and you have an energy density that is constant. So it will behave like dark energy in this sense. Also, they will need to have some pressure. So the idea is that these two theories will put together. Then you have several papers about these things here, and you have these dark energy black holes. That's in which the black holes not only increase their mass, but they also source dark energy. Okay. Also, you have to check if the abundance of this dark energy black hole is sufficient to explain the abundance of dark energy, and they claim that it is. It is if all the black holes, not only the supermassive ones, if all the black holes are cosmologically coupled. That's what they found. Stop. Now stop the work. Just a moment. Don't know why. and here. Okay. Okay, so just briefly, let's recall that within GR, you have that. Okay, now it's compact. It starts with a compact object in vacuum that's asymptotically Minkowski without an electron charge. The only solution is the Kerr metric. This is a theorem that you don't have other solution. If you are in GR also, but compact object in a fluid, which is asymptotically limit Hobbes-Walker, the exterior metric can be McVitie, can be Nolan, can be Sultana-Dir, can be Fadone-Jacques, another one, and several others, both known and unknown. There's no theorem about uniqueness here. If you also have that the physical mass increases, then you have a subset of this, and then you have the Sultana-Dir solution, Fadone-Jacques, and other ones. If you besides that, you don't have accretion, but the mass increases, then you have something strange that it was found observationally, but there is no, let's say, established solution apart from this work of Cadoni and collaborators. They found that indeed in GR this would be possible. But the only problem that Cadoni et al. Does not find exactly that k equal to 3, they find k equal to 1. So the point is that it's not exactly what was found observationally, but it's, let's say, at least qualitative close. Well, another possibility is only if you go to either you have new scalar fields or modified gravity to find this kind of behavior. Just to be clear, so what's the idea? This idea of Cadoni, just to briefly talk about it, they found that the mass indeed you have to be careful about what's the meaning of mass in this setting, because you don't have does not have a asymptotic flatness. You cannot use the let's say the standard ADM mass. You have to use another kind of mass, for instance, the Misner-Sharp mass. The Misner-Sharp mass is well defined in spherical symmetry, and they found that the Misner-Sharp mass increases with some. This is just a cosmological contribution. It's not that relevant. The relevant part is this one. This is something that depends on the internal structure of the object, but the main contribution is this one, which say that the mass increases linearly with A, apart from some correction here, but for some cases you can neglect this correction. So the point that you'll never be according to the solution, not to be A to the cubic case, but can be linear with A. Okay, this is just a brief comment about the work that I'm doing with them, in which we're extending this approach here, looking for in the weak field limit how this behavior, what happens here, in particular perhaps some application of dark matter. We are discussing this. But the essential point I forget to say, but the essential point to have this, you have to have a spherical symmetry with the anisotropic pressure. If you have isotropic pressure, there's no chance of having this cosmological coupling. So if, for instance, if these supermassive black holes are not true black holes, but it would be, let's say, exotic compact objects that have anisotropic pressure. Anisotropic pressure with spherical symmetry, I mean that the radial pressure is different from the tangential pressure. It's necessary that these pressures are different. Then they could be cosmological coupled. That's the idea that we are working with. I don't know why. Okay. So okay, I talked about this work. The Cadoni talk is more fundamental. I will talk now about this work here with Amendo, etc., which was published about in which we study the gravitational waves that comes from this kind of black holes. The idea is quite simple. Let's say from the gravitational wave itself, from the form of the gravitational wave itself, we will not detect this kind of coupling, because this coupling the natural time is cosmological, while the data from LIGO, it only takes a fraction of sound, a fraction of seconds, the duration. The duration is quite small. So we will not measure this kind of cosmological coupling in direct on the form of the gravitational wave. On the other hand, the gravitational waves provides relevant information. It's possible to constrain them. Talk about this. We can consider. Let's go to the next slide. Just a moment. Since okay, here. The major point is that from the gravitational waves, we can extract what's the mass of the object that collided. Okay, this is well known. This is data that LIGO provides us. But if this cosmological coupling is true, the idea is that in the past the mass was smaller. Okay, Moreover, we know that black holes are generated from stars. We are only consider black holes that came from stars, and the stars to generate black holes cannot generate black holes from any mass. You cannot have, for instance, our sun is not expected to generate a black hole. It is, and also the black hole has a minimum mass for it to be formed, which is about 2 solar masses. Okay, the minimum mass of a black hole that's formed by a star is about 2 solar mass. Note that you may consider primordial black holes that start with smaller mass, but it's not. This is not our purpose. We are only consider which is the standard case. The standard case is that the black holes detected by LIGO comes from stars. So the minimum mass is about 2 solar masses. This you can find theoretically with several arguments. Okay, so the idea is that we can look with the detection of black holes, the mass, we can have an idea what would be the mass in the beginning, and we will see if this mass is reasonable or not for the formation of black holes from stars. But to do this, we have to have an understanding of how these black holes form, and what's the time that takes from the formation of these binary black holes that collide and then lead to the signal of that LIGO detects. So this is the 2 main channels here of formation of binary black holes, in which you start with 2 stars. This is not a common process, but it's a process that can happen. It's not we start with 2 stars. One star takes the mass from the other, and then one becomes a black hole. Then one possibility is this common envelope channel, in which you have this mass transfer to the black hole, but first in a common envelope that has friction, etc. And then after this common envelope, then we end up with 2 black holes with a given separation here. For the other channel leads to a larger separation, but it also has different conditions. But the point is that that initial part is quite fast, because these need to be very massive stars. And so this depth of this very massive star is quite fast. But the point is that from the formation of this pair to the collision that leads to gravitational waves takes about giga-years. So this is the time that can probe the evolution of these cosmological curved black holes. And during this time, they are in vacuum. So they are not expected to be accreting anything. So just to have an idea, what's the distribution of this time here? The maximum binary black hole formation relative is about z equal to 10, because this is related when we find these stars that can lead to black holes. The minimum delay time, that is the quickest time that the black holes may have in order to collide them, is about 50 mega-years, and the larger ones, the maximum is about the age of the universe, essentially. Actually, you can also have black holes that are orbiting, and they will collide only in the future. But for those that we detected, it's about the maximum is about 2 giga-years. Okay, the distribution here you'll find from numerical simulations. You find it's about a log normal distribution. Log uniform distribution. Okay, it's distribution so that the log is uniform, so that you go to the original variable, you find this decrease here. So this is the data that we selected, data from the 3rd year of LIGO, LIGO, Cagra. So the squares here are M1, the balls are M2, the disks are M2. So these are the pairs. So here's the redshift of the detection. Here is the mass of each one of the black holes, the involved black holes. Note that this trend here, there's nothing to do with physics. This is just an observational bias, because for higher redshift, it's easier to detect higher mass. And that sample just did a selection to pick more confidence data. And just to have an idea what you can do, let's just pick one case. Consider just one pair of black holes. That's the data from one then. From this one, let's ask what would be the probability of this one to have an initial mass below 2. Since we know the distribution of this delay time, we can ask this question: what would be the probability that that it was formed with a probability below 2? What we find is that if you pick a single case, for instance, pick this case here. Okay, it's not this case here. The original mass actually it's here. The most probable mass is this one. Okay, the most probable mass is initial mass is also the most probable mass that you detect today. So most probably the formation mass is the same one that we're detecting today because of the type of the delay time distribution. But you find that there is still some probability of it to have a mass below 2. So if you only have detected one black hole, the answer will be just that this cosmological coupling as with k equal to 3 would be possible, and everything will be fine. Let's say we could not conclude anything. But the point that we don't have one observation, we have hundreds of them. Not 100, sorry, we have 90, exactly what we selected, it's about 90 of them. And then we can combine them and find there is a significance, in the end we find a significant probability that this cosmological black holes with k equal to 3 cannot be true because they require a mass that's below 2 solar mass for that formation mass. Apart of that, we also know that the LIGO itself has observational bias. As I told you before, since we detect some, actually we only allowed to detect a few of the low mass black holes, binary black holes, because it's easier for LIGO to detect higher mass. So the point that here's the distribution of the events, a smoothed version of the PDF now for the detected events at LIGO. We're using the 90 events that we selected. So you'll find here, we can see they have mostly are here with this mass about between 30 and 40 solar masses. But actually what is expected that most of the binary black holes that exist are here because there is observational bias that makes it harder to detect this thing here. So this is this is a standard profile which describes the distribution of mass of binary black holes. Let's say the true population of binary black holes, not only the population that is detected by LIGO. So the idea is that you can use this population here also to put constraints on this cosmological coupling. The idea is the following. So this is what's the population observed. This is the expected population. By the way, this is the PLPP profile, the power law plus peak profile, which is a well-known profile within binary black hole community. Let's say if there is no cosmological coupling, by the formation of these binary black holes, the distribution of mass should be exactly the same of the PLPP. But if there is cosmological coupling, the distribution of mass should be something different, should be deformed. And here is an example of one of the things that we find. So the initial mass includes, there are many black holes that will have a mass below 2, will be close to 0. So this, I just skipping many of the technical details, go straight to the conclusions. So in here we do a plot with K versus minimum black hole mass. So you can see that, as I told you, that observational papers of in the beginning of previous year say that K should be about 3, but we found that if this K to 3 is valid for LIGO or binary black holes, actually this will be this is only possible if the minimum mass of these black holes is below or about 1 solar mass, which is we have no model for this. If you require that the minimum original mass should be above 2 solar masses, then we find that K, this is reasonable, then we find that K should be below 1.1 at 2 sigma level. So this is the line here that show this, consider this minimum mass equal to 2. Okay, so that's it. So consider current data should be here. This is just because we did here 2 methods. One is what's called direct and the other the PLPP. But the PLPP just extends, is just a bit more stronger because they consider the true population. Not that is eliminates observational bias. Okay. Okay, general remarks, conclude? Yeah. To conclude, so chronological black holes are not a novelty and do appear in some GR solutions, okay? No solution satisfies M proposed to AO cube as suggested by Vaha and all this paper here. We don't know how to generate them. Closest case seems to be the case of Cadoni that requires K about 1. K about 1 is not eliminated according to our analysis. It's a possibility. We cannot And we found, this is just what we found, just to restate here. Okay. In summary, according to that, with the consideration, provides strong constraints for cosmological black holes. So if you use this gravitational wave data from LIGO, Virgo, Kaga, these are strong constraints. Future observation, this year actually can quickly enhance the bounds we find for K greater than 1. Theoretically motivated CCBH parameterization need further work. Okay, we are actually, this is one thing that we are trying to understand more these solutions. Okay, so I stop here. Thank you.
So I will save the questions for the discussion part. I have many questions, as a matter of fact. But we are tight on schedule, so we have I think it's the last presentation for the day before the discussion section. Yes, which from Mariana, and very interesting talk, Levi. I was lost thinking about my questions. So Mariana, did you put your presentation? A apresentação da Mariana tá ali no... Please, Mariana.
Hello, everyone. My name is Mariana. I'm a PhD candidate at Valongo Observatory under orientation of Karim Menendez and co-orientation of Tiago Signorini. And I'll talk about protoclusters. Protoclusters are the early stages of clusters. They are progenitors of these structures at high redshift. Here we have a picture to help visualization. And wait a minute. Okay, and this is a dark matter simulation. And we see that protoclusters are sparse structures at high redshift. You can see here there is clumps of matter in overall this region. So this is a sparse structure that has not collapsed yet in a massive core with masses greater than 10 to 14 solar masses. And at redshift 4, it can reach scales of 10 to 14 Coulomb megaparsecs. And they are challenging for identification because they don't show the cluster features like a red sequence of galaxies or the hot intercluster gas. So it's kind of difficult to find them by eye. Because they are very spread structure. We also find a small density contrast when we compare this to the field. And so to overcome these difficulties, we can use Bayes tracers. The point of Bayes tracers is we expect some objects to inhabit massive halos, and then we use these objects as targets for protoclusters. There are few traces in literature. You can find radio galaxies, quasars, but here I will talk about submillimeter galaxies. That is what we use in this work. Submillimeter galaxies are galaxies very luminous in the infrared. They are dusk obscured galaxies at high redshift. So we measured this in the submillimeter band here. They have high star formation rates, like 100 to 1,000 solar masses per year, and they have high gas mass too. So we expect them to inhabit density peaks. If you go to the literature, you can find works reporting SMGs associations at tracing massive halos. And also we can find SMGs in fact, tracing protoclusters. This is the great, most of the works I have seen, they are reporting SMGs, in fact, tracing protoclusters, but we also can find SMGs in filaments and or even in less massive environments like cluster groups. So we would like to contribute to this topic. What kind of environment do SMGs trace? And here we have a picture of Cosmos field. And Cosmos field has been extensively studied, and we know that we have many detections of submillimeter galaxies in this field. And The idea is we select 1 submillimeter galaxy in this field at redshift 4.5, and then we are trying to see if we can see an overdensity over this region. But what kind of source should we look for this overdensity? We have many sources, like we have Lyman break galaxies, we have radar galaxies, we have what kind of sources do we like to do this? We choose Lyman alpha emitter galaxies that are emitting the Lyman alpha line. These are typical star-forming galaxies, like masses to 10 to 8, 10 to 9 solar masses. They're representative of a low to moderate mass galaxy population, so they are quite common in the universe. We can detect these objects at in the optical range, because when the Lyman alpha line is emitted at redshift 4.5, we can detect this here in the optical. And Lyman alpha emitters also includes a population of young galaxies with faint continuum. This is very interesting. I'll show you this about this in the next slides. So if we want to answer this question, what kind of environment do SMGs trace, we should answer if we find a Lyman alpha emitter over density in this region. So how can we detect Lyman alpha emitters? There are many ways, a few ways, but here we use 2 filters. We have a narrowband filter and a wideband filter. If we have an emission line here, because of this small range, the source will look bright in the narrowband filter, but if we measure the same emission line here with the broadband, this will be a faint source or even be undetectable, depending on the strength of the line. So we can, using these 2 filters, we can select the Lyman alpha emitter candidates. This narrowband has 65 angstroms, and this allows us to probe a region in the redshift range of 0.03. For the wideband, we use the AirPlus Supreme Cam. So as I told you, Lyman alpha emitters can be detected as narrowband access objects in the sense that they are brighter in the narrowband than in the wideband. But we also can measure interlopers at low redshifts, like the O2 emitters at redshift 0.8 or O3 emitters at redshift 0.3. And this is the kind of sources we want to get rid of to get an accurate measure of the density of the region we are observing. So let me tell you about the data. This was our team made narrowband observations. In the IMAX, in Las Campanas Observatory, it was 4 nights of observations, and this was a total of 300 ship images. It was a lot of work to do the reduction, the calibration, to put all these things together to see the whole picture of the field. And it's just one slide, it's so sad. And we also use the wideband images from Supreme Cam, from AirPlus band, from the Cosmos survey. And this you can download from the website if you want. We have 7 spectroscopic detections by our team with the IMAX telescope. And we also use the Cosmos catalog in the R-band for the photometric redshifts. So just refreshing the methodology, we use submillimeter galaxies from the literature as a target for a potential protocluster region. Then we search for typical star-forming galaxies, the Lyman alpha emitter galaxies at this SMG redshift. It's a narrow interval of in the redshift, it's 0.03. And the field of view of IMAX allows us to probe a region of 60 co-moving megaparsec. Then we calculate Lyman alpha emitter density in this region and compare to Lyman alpha emitter density in the field in that similar redshift. And then we estimate the descendant structure at redshift 0. So this is the way we select Lyman alpha emitter candidates. I told you they are narrowband access objects. So we have the images. We make a 2 arcsecond aperture photometry measurements in the narrowband and the AirPlus images. And then we extract the magnitudes and we can make a color magnitude diagram. So we expect the objects that are not emitting a line to have a color 0. And we expect the ones that are emitting a line to have a positive color. But we also put other constraints that we use. We want sources that are emitting an equivalent wise greater than 80 angstroms, because we don't want faint objects that was incomplete data. And there is also this orange line here that is the 3 sigma in each bin of narrowband magnitude. And this is because we want this narrowband access to be produced by a real line and not by a small variation in the continuum of the sources that could produce a small color. So this is what it looks like in the sky positions. We have these blue dots here. They are all narrowband detections, and that we could also measure the magnitude in the R plus image. And these pink ones are the ones that Sextractor could not give us a reliable magnitude, so they are just narrowband detections. After doing the color selections, we get the selected sources. And then made other things like cross-match with Cosmos catalog to eliminate low redshift interlopers. And then we get these blue triangles that are the Lyman alpha emitters at redshift 4.5. These red squares are very faint sources in the R+, and we could not find them in the Cosmos catalog, so we don't know the redshift. And these are the sources that I told you before, that we just have the detection of the narrowband. So after doing the cross match and eliminating interlopers, we get these sources. And we could, I had to check the cutouts. Cutout is just, you cut the image at the position of the source to see if the source is real or if it's like something, a light from saturated stars of the fake source. So after checking cutouts, we got 86 Lyman alpha emitter candidates. And here I put the cutouts for you. This is just a sample, a small sample. That we have 3 sources here. Here you can see the narrowband, a source in the narrowband, and you can't see this source in the R plus image because it's faint. It's like that kind of object that I told you that are young galaxies that don't have a bright continuum, but you can detect them, the Lyman alpha line with the narrowband filter. So that we have other sources here. You can find a little more bright, and here is a bright source in the broadband, and this is an AGN candidate too, with it's consistent with the redshift, photometric redshifts of AGN. So I made a density map, and in this yellow region here, you can see number over density. Let me tell you what is a number over density. Is you can calculate this with the Lyman alpha emitter density we observe, minus the Lyman alpha emitter density in the field, and this Lyman alpha emitter density in the field we can, I calculated from the Auchi work. There is a review on Lyman alpha emitters. And I got this 3.6. And if we go to simulations, we can see what kind of structure it will be at redshift 0. And if we have the 3.6 is like here, it's a little greater than 14.5. This is in the log. So it's like a medium mass cluster like Virgo. But there is something pretty interesting here, because there is a literature, a protocluster right in this redshift, and it's just a little below this structure that we found. And this is called the Talaray protocluster. So it seems like we found the extension of this bigger structure. So what we found is that the SMG is tracing a moderate mass cluster at this redshift 4.5, but it's not inside the peak of the density, but it is at a distance of 13 megaparsec from the peak density. And that's it. Thank you.
Can you hear me well? Okay. So you have any questions for Mariana? Or we can already start the discussion because this is the last section of the day. So Any comments? People online, do have some message from the chat. Can you? Okay, Cristina.
Very nice talk, very nice work, Mariana. Can you go back a few slides where you compute estimate the mass this structure should have in redshift 0 you mentioned? Yeah.
What slide? Repeat, please.
Yeah, what is the mass that you expect this protocluster will have at redshift 0? This what this plot
Okay.
is showing, right?
10 to little greater than 14.5, like less than 15, but in the middle of this, just like we have the number over density of 3.6. So just like this, and we have a error bar here.
Okay,
So
and
it's like here a little bit.
okay, and very interesting that it seems to be a part of another structure and your plot from the next slide. And if you consider that, what the mass should be, based is the same over density and expected
We'll
to
look
have
at this with more careful, but I say what will happen if this will form an only structure, of it will get an evolution in a separated way. We don't know yet, but we are going to look this with more careful.
Oh, that would be very interesting.
I'll do this right now.
Okay, great. Thank you.
Thank you.
Thank you. So any other questions? Martin, I think you had a question, right? Please go ahead.
So do you plan to extend this kind of search to other wide field surveys in the submillimeter? What are like the limitations, I know, flux, resolution?
In the
For the submillimeter galaxies.
For the submillimeter galaxies, yes. Well, we have bright submillimeter galaxies in the cosmos field and in other fields, but the thing is we need the narrowband data. The narrowband data, there will be a release of narrowband data, I think in this year we'll have the narrowband. And actually, even for this region of the protocluster, for Array, that will be interesting to see if we can find the narrowband in this structure too, for us to understand what's happening there. But the more difficult thing is to have the narrowband data. But we have a release, and we can extend to other regions to see. I haven't planned this yet, but yes, we are just focusing on this to finish this region first. Yeah. But what do you mean? Using Lyman alpha-meters? Yeah. We can look for this, but right now I'm just focusing on this, but it is a possibility. It's possible to do this. Yeah.
Okay, so any other questions from both online audience or in here? And as I suggested, I think we could also start the discussion together as the last session. And we skip Davi questions.
So thank you.
Okay. Martin, do you have a question?
So a question for Davi. So I think it's very interesting that you are taking seriously this cosmological couplet thing, and maybe you're ruling it out. But going to the very basic, there's something like very basic question, and is also connected to something that's been discussed in the literature for decades and so on, which is about the scale problem, right? Because if you think like, okay, I have a black hole and I want to couple to Friedmann-Lemaitre-Robertson-Walker. Fine, you can find a mathematical solution. But I mean, the surroundings of a black hole are not Friedmann-Lemaitre-Robertson-Walker. They are in a galaxy. We are not matching our solar system with the universe. So there's a lot of discussions about this, like cosmological influence on small scales, how you get to like basically point stuff like stars, which are zero Ricci. They have Vio tensor. They have no Ricci tensor, and then you get to something like the Friedman-Robertson-Walker, which is zero Vio and Ricci. I mean, all these averaging thing. It seems that they are like use Friedman-Robertson-Walker to describe very large scales, and you put perturbations on the top, and it seems to work. But then you don't expect to connect to something that's really Friedman-Robertson-Walker in small scales. So I mean, these solutions, they seem meaningless to me, but maybe there's something too basic.
For the record, I think David Ting is ruling out stuff.
Yeah, I know.
That's what he does.
No, but anyway, no, actually, this question is very important. By the way, before I start that visit to Germany last year, I saw the abstract of the first paper. I read the abstract and I thought, no, this is meaningless. Let's forget it. And then as soon as I arrived, Luca proposed, let's discuss about this. Let's do something on this. Why? Okay, but let me develop for the on your question. Actually, my main complaint at the beginning was very closely in line with yours. Essentially, the following: it's for sure it's true that asymptotically flatness does not exist, because when we know that if we go far away, at least if you go far, it will find a cosmological Friedman-Robertson-Walker. So in this sense, okay, I agree with the authors that it's not exactly Friedman-Robertson-Walker, but on the other hand, they're doing too much. They are going too far away in the sense that if okay, that's asymptotic is not exactly Friedman-Robertson-Walker, it's not exactly Minkowski, but much before Friedman-Robertson-Walker solution, you have a galaxy, for instance. In general, commonly, black holes are not isolated in the universe. You have first a galaxy, or you can say about beside the galaxy as a whole, you also have local structure. You have other black holes, other stars that are nearby and they are perturbing space-time. So, okay. So one thing that to be more realistic, I would say that the first thing, if you want to consider some kind of structure far from the black hole, the first thing, at least one good point to be considered, what about can the space-time of the galaxy generate some different solutions? I think that would be an interesting thing to consider. Okay, so what about what's the role of this coupling black holes with cosmology? What's the values of this? First of all, it is a good, let's say, thinking experiment, in the sense that we know that the cosmological solution, we know the black hole solution. It's in principle possible that you have an isolated black hole in a cosmology. This is in principle possible. So that should be this kind of solution. If there is no this kind of solution, we should find what prevents us within GR to find this. And if you can find that there is something that prevents us to do this, that's something physical. That should be. My point is that studying this case, it's important in itself. Studying if a solution, you have a local structure and the cosmology, this is important. Even for instance, you can also consider the case in which a black hole is generated in a galaxy and then is ejected and go to in the middle of nowhere. So you have, let's say, essentially a black hole that fills the there's no local structure. It goes straight to it goes straight to cosmology. But anyway, okay. So my point is that one, theoretically, it's interesting to do. I think it's not only it's important to do it. This is something that someone needs to deal with this problem. It opens understand of how to understand mass without asymptotic flatness. It deals with this issue. And another thing, it opens the way in order to go to more, let's say, realistic settings as well, in which you have not Minkowski, but you have some kind of perturbation. So there are some papers in this line that claims that this solution, where you have asymptotic Friedman-Robertson-Walker, is more real. They are more realistic. This I don't agree. I don't think they are more realistic because they are this way. The point that from the theoretical side, the point that they implement something that is useful for understanding, and they are find something that is, let's say, radically different. No one, in the sense that it was not expected to find some kind of mass increase with cosmology. But on the other hand, it's important also to stress, as I tried to stress in the beginning, that if you have a local structure that is within cosmology, that structure can fill cosmology. It's not because it's local that cannot fill cosmology. Even GR, there are exact solutions that show that this is possible. The thing that you can ask is, are these solutions real? I would say for sure they're not exactly real, because usually black holes is inside a galaxy, and so you feel first the space-time of the galaxy and then other things. But let's say the development is important, and anyway, in the phenomenologically, it is increasing. It's remarkable that they find the supermassive black holes are increasing their mass with 8�3. It's maybe okay. This is one possibility. Maybe other things. But this is one possibility. So let's study this case. So that's indeed, but indeed, our as Clasio said, in the end we are ruling out. But and also this idea that black holes can generate dark energy. I could not develop much of this, but this is okay. It's hard to be true, but it's interesting idea also. Perhaps exploring this further. But okay. I comment. I don't know. Could I answer your question?
Forever.
Okay.
You could argue for the time scale of a merger of a binary black hole.
Okay.
Anyway, I have a comment on that. You said that it's okay. You assume the black hole is isolated somehow, right? In the supermassive black hole scenario, this is simply not true. There's a lot of things going on in the galaxy, as most of us know. But for compact mergers, there's a lot of discussion of deformation channels, and there's a known offset, at least for the short gamma ray bursts, which are related to the kilonova, at least. There is a offset between the galaxy and the short gamma ray bursts. So this might indicate that there are many compact objects just happening in the halos or isolated from the galaxy. So not that crazy the idea that we are. Yeah.
In any case, it's the galaxy and the black hole. So probably the galaxy is much more important than the rest of the universe. You know, it's so.
Yeah, you still don't have isolating the terms that have Friedman or Robson Walker just on the corner, right? You are embedded in the halo. There is some discussion, and we are actually working on that. If these are ejected, is are commonly ejected or not, right? Depending on the mechanism. If it happens in globular cluster or not, but there's a kick. There's an important kick, at least for the population of mergers detected by the LIGO, that could, in principle, eject the mergers outside the galaxy. But still, yes, you have a fair point on that. Any other comments?
It's a common question, truly exposing to the exposing my ignorance in this subject, because I was looking at Farah's paper, and I understand the importance of looking at elliptical galaxies is just to try to ensure that there's no continuous merging on these objects.
Yes.
Okay, so that's what they're calling. Is that what we're terming isolated? Just the fact that they're not.
Yeah, they are looking for cases
accreting.
with the accretion is negligible. Yeah,
Okay.
that's what they are looking for. Yeah.
So I apologize to myself really here, but my understanding, I mean, the idea is that the expansion would be the expansion of the universe would be altering the measured mass of these objects.
Yeah.
Because my
Yeah,
understanding was that
Yeah.
when I talk about expansion,
Yeah.
I say, oh yeah, but in the smaller scales, I mean, you don't have things getting more separated from each other. I mean, things that are gravitationally bound.
Yeah.
So I mean, apparently there's some
No.
basic thing here that I missed.
No,
Because to me, it doesn't make an.
Okay, I will answer in this way because otherwise my neck will hurt. Okay, but no, that is not let's say intuitive. The essence is that for instance, mass is commonly defined as an ADM mass, which requires that you consider asymptotically flat backgrounds. So the idea is that it could be that if you consider that your background is now non-asymptotically flat, it's a Friedmann-Haber-Sokal one, somehow local structure would fill this cosmological one. That's the point. So is it possible to, so one has to compute and see if it may fill. And then also there is one question that we also ask. Okay, so suppose that black holes can fill this, but we know that standard method in principle has no reason for that. So we need some explanation why black holes would fill and other does not. But suppose that black holes would fill this kind of different coupling. So the mass will depend on cosmology. But the point that there is not is not to be something that you find let's say intuitive, because it's not that the mass is entering the black hole. That's not the idea. The idea is that the black hole mass depends on your boundary, on your asymptotic, how this behavior. Okay. So this is their idea. Okay. So to be clear, fundamentally, as I discussed with Martin, there are things that are not well understood. There are different approaches to this. So one of the approaches is from let's say from a fundamental one. Let's consider theoretically consider a black hole into has a black hole and pure cosmology. Find how its mass evolves. And this is not a trivial question because there are several solutions. There's not one theorem that says that the answer is that. And there is another approach in which there's more observational related to this work of Farah, also Crocker and collaborators, in which they do a more phenomenological side, also, and they consider how the black hole in particular, the supermassive black holes are evolving their mass. And they find, this is their work, in which, for some reason, the black holes are increasing their mass faster than expected, consider the mass that they can accrete. And it's not a matter of a factor of 2. They are creating correlated with the expansion of the universe. Wow. Yeah, that's what they say. Yeah, that's what they say. It may, okay, that's a, okay, it maybe can be something wrong in this observation. For sure, there can be something wrong. But the point that up to now, I don't know anyone that said that it's wrong. It's not a clear explanation. I read several papers. Up to now, there's no clear say they missed something here. And if you adjust this, everything goes fine. What I have heard also talking to others, that there's some unknowns that perhaps there's the explanation, but they don't state something that correct this and everything goes fine. So that's the point. I don't know if I was clear.
No, I need to look. I mean, I know there's a lot of discussion on how galaxies, this relation of the supermassive black hole and the galaxy, the spheroidal mass, and how galaxies get into that. And I mean, there's quite of first you grow the stellar the stellar mass, and then you accelerate on the growth of the supermassive black hole or the country. So there's quite a bit of uncertainties there. But I guess, I mean, by taking quiescent galaxies, the idea is that they're not accreting anymore, this black hole mass. But that was really interesting. I wasn't aware of that connection. So
indeed, yeah, if it was just, let's say, a to the power of 0.1, for instance, it would be okay. That can be it can be easily some observational mistakes, simple. But it's 3. Wow. So not to say that's right, but let's say cause more attention and.
Okay, thank you.
I don't know. Any other comments, questions?
Maybe like I don't know, maybe soon to ask the question, but like I guess if you consider an evolving value of W, then the value of K for the evolution of the black hole mass is gonna evolve as well with time, right?
You mean the evolution of the number of the K? If you perhaps K, it will be, let's suppose that in the beginning of the universe, K would be smaller and then it becomes larger and larger. Yeah, that's a possibility. Indeed, we have not tested anything like that, but with the point that we don't have any model for that or any observational suggestion for that. If there is some, by the way, in our talk, you consider the case of gamma that changes cosmologically. So indeed, there are modified gravity models in which gamma, the gamma ppn, can indeed change cosmologically. But in this case, we don't have a model for that. From the fundamental perspective, we don't have a model that goes equal to the k. We don't have this model. We only have observations that suggest this. The closest one is that work of Cadone, that's awesome work now, in which k is exactly 1. Okay, so and curious, it's the case that we could not rule out. That's not to say that's impossible to rule out. There's that our approach does not rule out.
I would say there's so many things going on before you expect K to vary with time, right? So to consider. If you do find this, I mean, it would be very compelling, right? Because it's another free parameter without motivation.
Yeah, but indeed, perhaps someone develop, perhaps this case of Cardone itself will develop more and find a different kinds of form expression of the cosmological coupling. Perhaps this case will have some time dependence, for instance, and then we will have a motivation to proceed further. But up to now, without a motivation, it does not seem to be a purpose on this.
Okay. So any other question, comments? Okay. Martin, but I'll skip Martin because I have a question and I didn't have the chance. He's taking out the discussion. So in the case of still in your case, I don't one thing I don't understand. You consider black holes from 2 solar masses, but there is a mass gap over it.
No, it's
right between 2 and 5.
Between 2 and 5. Yeah, for sure. There's the mass gap of black hole.
But you still
just to be more conservative in the case that is allowing for more chance for these cosmological black holes with k equal to 3 to exist. So if we put the constant of 5 solar masses, our constant will be much higher, would be much stronger.
Okay.
So the minimum. So if let's say, so we find that, let's suppose that for some reason the minimum mass of a black hole is 1 solar mass. Let's suppose that we have some theory and we can find. In this case, k equal to 3 k equal to 3 is not ruled out. Because as we're going
the last
down,
result you show.
As we're going down to the mass, it's more probable. The point is that we are testing. Consider the mass that you observed some data of LIGO, etc. What would be the initial mass? And consider that the initial mass is not arbitrary, there's a minimum value. So we find a constraint. If the minimum mass is 0, then there is no constraint.
Okay. So following that thought, what would happen with the neutron star in the limit of the mass gap? Would they evolve with mass too, the neutron star?
Good.
Because in this case, they would turn into a black hole into the mass gap. It could explain the existence of a mass gap population.
Good. Actually, there is a paper about that. That we use this cosmological coupling in order to try to explain the mass gap. I read in that paper. My impression is that they answer in part. They indeed they show that there is a mass gap. They use this to generate the mass gap. I can show you the paper and then we can discuss. But indeed, they use this idea to show a mass gap. I would say that they have other problems. For instance, they have this problem that we're talking about. But it's indeed there is this idea, yes.
Because that's a real issue, right? The mass gap and how to explain.
Yeah.
Anyway, so Martin.
I have a question on a totally different subject. So if anyone has question on that subject, maybe you should go. Okay. So I have a question connected a bit what Carlos presented yesterday and what Vitor presented today, which is we tend to think that the, let's say, traditional analysis of strong lensing, whereby you take the light distribution of image and find some optimal solution for the lens and the source. We tend to believe more on that than maybe training, machine learning, like a neural network with normalizing flows or whatever. People tend to be, let's say, conservative in that sense that, okay, I'll do my modeling. I know the physics. the other stuff doesn't know the physics, just learn the physics or learn something that may not be the physics. So I believe in my tool, which uses the physics to build in, right? I think that's the reasoning. People can disagree. Now there are a lot of other things that go on top of that in the real world, like noise, like interlopers, or even that's a strongly nonlinear problem. It doesn't have a unique solution. You also have like a kind of a loss in the traditional modeling, like you have regularization of the source, this Vernon tessellation. So at the end, there are some hypotheses that. So my provocative question is, are we sure that doing the, let's call traditional way, which we are sure about the physics, but not about everything, and the machine learning way in which we may not be sure that the system learns the physics, but which we can train with a ground truth, are we sure that this is worse? You know what I mean? Are we sure that we should always believe in the traditional modeling in contrast to the machine learning one? That's a provocative question. We can discuss more, but I would like to hear opinions.
So I would say there's like Tao Te Ching says in the book, there's a tree. The wise man has a tree, a middle way, right? Which would be, for instance, has a physics-informed neural network. Well, there's a lot of tension between communities where some people just believe in what the data says, and people believe what physics says, right? When you are working on data-driven things, especially with images, you are very, very limited to the quality of your images and how you are able to simulate them. So that's what Vitor is facing, right? And this will always have some people not really believing it on the final results, right? So in that sense, what we do is, okay, so we can beat in terms of velocity. So we can have a very good approximation on a lot of things, and that's what people are trying to do in several years from now. But with the neural posterior estimation and other kind of techniques, we're starting a phase where we can actually build very well calibrated PDFs, where you can test the confidence of the PDFs, and people start getting, okay, that's sounds good. You can make a likelihood free inference with controlled simulations. So that's a step. By the end of the day, you could also input the physics inside the neural network, which I think is a third part, where, for instance, you don't make a loss function to exactly minimize your targets, but you can make a fast inverse modeling, actually, building a loss where you constrain a physical model and turn back, resimulate the thing and see if it matches with your galaxy. That could be, I don't know if you understand what I say. So you just produce a model that will make a simulation and will match the galaxy. In that sense, I think no one could actually make a criticism. So you are actually using the physics and mix them with the neural network that extracted the parameters the first time and work it. So at some point, I think the things you go into that direction and everyone going to be happy. You know, that's what I would say. So does anyone have any thoughts? I don't want to finish the discussion.
Why people think more questions? Yeah, no, I now to make a joke, you follow the Tao Te Ching way. We can follow the Galilean way. Like, let's do experiment. Let's have a data set where we know the truth. Like, let's say, I think the problem is the size of the samples, right? Like, for example, Carlos has this realistic simulation where realistic means that the lens is more realistic, right? Not necessarily the images are so realistic. I don't know. But in any case, it's like a very small sample. In this very small sample, you can do a lot of detailed analysis because it takes time, but it's a small sample. But let's think that we could do something like faster and people in the community at both from ground-based and space-based data, they are willing to, they are trying to do more like automated pipelines. Like João has his pipeline, like Shajib, Anwar Shajib has his pipeline, and this Dolphin, and maybe there are like about four-ish pipelines worldwide that try to get a lot of lenses and model them automatically using the traditional way. So yeah, but of course, people are focusing on the data, so we cannot tell what's better. But like something like this on the simulations, so that, I mean, the Galilean way would say just do a lot of simulations and see what performs better at the end, right? With the current networks, not with the like physically informed networks that will convince people conceptually, but try to see what the results are empirically now. That would be like maybe a way forward that we have the tools ready, right? We I mean the community, but I mean this group too, have the tools ready to do that, right? And like empirically checking with a large enough sample, if really the traditional modeling, which takes much more time, we know, but if it's really performs better or equal or worse, or, you know. Oh, Carlos.
Carlos, can you please comment first?
Sure.
Carlos?
Just a hi. Are you hearing me?
Yes.
Yes.
Yeah. Just a quick comment, because I think that Martin has already touched this point. I think that with the current models that we have in terms of machine learning in these things, we may use these two approaches, like machine learning and parametric ones, for different purpose. Because if you're interested in modeling a galaxy in details and know their like dark matter properties and do the reconstruction of the source and investigate these things, I think that in terms of what we have now, we need some old-fashioned way of modeling these things. Because as far as I know, these machine learning techniques, they focus more on simple models, just a few parameters. And if you increase the number of parameters, this is the best of I know. Maybe someone can comment on this. But if you increase the number of parameters, like include dark matter things and other properties, and try to reconstruct the source, these machine learning techniques are not performing very well, neither in the simulated data sets. So I think that nowadays we can make use these two techniques for a different purpose. If you want to just infer the ascent radii, because this is relevant for your work, maybe using this machine learning technique is way better, because you will model your sample much faster. But if you are trying to infer properties of the lens galaxy, or trying to reconstruct the source, maybe you can use the traditional methods, because you have different science in mind. I don't know if this adds too much to this discussion, but yeah.
Okay, I have a quick comment on that. As a matter of fact, well, I never try many parameters in the strong lensing model. Just the first disclaimer on my message here. But what I do know is that neural posterior estimation scales very well with many parameters. That's actually one of the reasons to use it, to avoid Monte Carlo sampling. If you have many parameters, let's say 10 or 20, you actually have a great advantage of using neural posterior estimation, because you can do it super quickly. So I don't know if it's going to work, as Carlos just mentioned, but I know it scales well with time. So if you have very many parameters, that's one of the reasons to go for neural posterior estimation instead of traditional MCMC, right? So that could be helpful. But the way Carlos is stating is that, you made a quick and dirty estimation with AI, and then you make detailed modeling with traditional techniques where people believe what they are doing, right? Yes, I think that's what people are trying to do right now, right? But I think in scale, there is a disadvantage if you need many parameters like a 10 or 15. It will take way less time on doing this with AI techniques, physics informed or not, but at neural posterior estimation. So that could be an advantage in the individual basis if you are making detail. This could make a difference. And just to answer Martin comment, well, yes, the path that you propose is a secure way of addressing these questions. But as we are we are starting doing philosophy here, I would say Thomas Kuhn, an important scientific philosopher, would say that science is about people, right? So, and what people believe and expect. So if we do that way, we just validate over the data and say, take it on your face. This works. Accept it. Many people will still have some. You will not fully consider the solution. But yes, in terms of scientifically addressing the question, I think you're right. That's the easiest and quickest way of doing it. Right? But sociology is part of physics. Cristina, please go ahead.
I would like to make a comment on what Leslie was saying. Actually, a question first. You mentioned that using this neural network approach will be much efficient when you have many parameters, like 15 or 20, which is the case of like the modeling Carlos is doing. But what about on the simulation side to create all these simulations to train those networks, which many parameters like this is about the same time, or we need much more time to do that from the simulation side? You mentioned for training, it's okay, but
I don't know if I fully could hear you well. Did you hear you well?
Yeah, the sound was not very good, but what I think I understood was about if in the simulations we can vary enough all the parameters so that we have like a large sample enough of a large sampling enough of all this variety of parameters, right? Was that the question?
yes. And what about on the simulation part of this approach? You have a larger sample to train all the networks.
So, yeah, I don't know I mean I know like where we want to get to, which is that if we really want to measure more things, we want to have even much more larger samples, because we do want to probe this parameter space of all these parameters and still have a sufficient number for the training, right? I don't think
Exactly.
there's a limit to perform these simulations. I think they are cheap nowadays. So if you have 60,000, somebody mentioned at some point, but I think nowadays, why not having 60 million? I think this is not a problem. And so, and I think maybe we are not doing that, but we should maybe go to really large samples like this. Why not 60 million instead of 60,000? Maybe next stage. Classy was asking about suggestions for the next challenge. Maybe next challenge should really be more massive in terms of data also, right?
Yes, I mean, no, computational time is not an issue, as you said. It's easily done around. I got these numbers. I don't remember by the top of my head, but within a day you can make more than 100,000 simulations, and they can live inside a regular computer, not a regular computer, but a good computer at least. Okay. I would say, why not go 6 million? The reason is variety. I'm not completely sure that the models has enough variety to justify 6 million, for instance, right? Because most of these simulations are done with Galaxies strong lensing. So there is no interacting galaxies, there are no pairs, groups. Clusters are complicated. There is cluster simulation, but not many, and most of the simulators doesn't really do a good job at working on them. But if we can justify the variety enough to make 6 million, for instance, I think that's completely feasible for a cluster to handle it in maybe a week or two, you know. So I think that can be done. It's just needs to have justification to go so many simulations, right? 100,000 simulations seems enough, at least for the idea of finding strong lensing, right? What would concern most in terms of finding strong lensing is actually how to make very good artifacts that will mostly be considered as lensing in the strong lensing finders. Right?
Yeah, okay. And as Carlos was mentioned, depending on the science you get and the data you have, because depending on the quality of the data, you can try to fit better models. And that will depend on what you want. I understand you are dealing with large, to apply these methods to large area surveys, photometric surveys, so where the quality is not as good as like space-based images like the ones Carlos is using. But yeah, I was just wondering, to answer your question, depending on the science case you want and the quality of the data you have available to do the modeling.
Okay, thank you.
I wanted to say something about Classio's answer. One important advantage of using simulations to train a neural network is that you don't need a fixed data set. If we're working with simulated data, essentially at every epoch of the neural network, I can just simulate new data as long as I have the parameters well constrained. So I think this debate over if 60,000 is enough, maybe 600,000 is enough, this can be, you don't need to focus on that, because if you're using simulations to train, then you can just train until you can set some sort of target with your loss function or some other thing in the network, and just allow the simulations to run until you get to that point where you reached your target. You don't need to worry that much about the size of your data set using simulation-based inference, exactly because it's cheap to simulate, so you don't need to have a complete data set beforehand. You can just simulate new images at every epoch of the network.
But this is for modeling specific with simulation-based inference, right? I think maybe Marcin's question was more general, or validating stuff with other algorithms. Right. But you are correct. Any other comments, discussions? It's 35 minutes past midday, which means many people might be hungry. At least myself, that wake up very early. So any other comments, people? Or any other subjects? We were touching the machine learning stuff, but we didn't pretty much say about the future of LastBeru. If someone is willing to make a comment over it. No?
So it's a comment on your question, but it's also a comment on our organization. So the idea for today and yesterday was to have some subjects. If there's no discussion, we can throw them to have the discussion, and that's pretty much worked. But next on Friday and Thursday, the discussion sessions, of course, they are open to everyone. Come. But there, it's a bit a different philosophy. It's a bit more like what can we do together? So when we say the future of LastBeru is like, okay, do you want to get involved? And for example, we know Delve is a very large survey, important. It was not available when we did this, The last rule we want to incorporate. Okay, we will have a hands-on on how to use the SLComp interface. So maybe people will want to by themselves go and grab the Delve data and incorporate into the Raspberry. So that would be great, of course. And the idea is that this software is shared. So that's one example, I mean, of getting involved, right? There is the tagging and classification. You have a hands-on about that, but then we have people, if they want to get involved, really, they can. There are more open-ended things in the same also, like, for example, how you feedback the information we are learning about the systems on the database. For example, now you saw João is modeling a lot of systems. He has his table. We have the last Raspberry. How we feed this back into. We have the classifications, everyone that will classify and tag, how we fit. So there is things, it's a mixture, of course, of scientific interest tools and a lot of like technical things like database, etc. This is not like, as of now, this is an effort which is really mostly this group. But for example, in the strong lensing science collaboration of LSST, there's a lot of interest in those things. Other people have done things that connect to this, the different. So there is a lot of discussion on how we try to make things uniform, how we maybe have a standardized way of reporting the model fits, maybe how we share objects. So how to build an interface that's scalable, updatable, that we can add information. So there are a lot of things regarding the last Raspberry. So if people want to really have this discussion, just to get informed or to contribute, then there is a specific slot on that. And the same for machine learning. We heard a few talks about machine learning, maybe just Vitor's one actually as a talk. We will have a hands-on by Vitor again on Thursday. So a hands-on on the regression with machine learning, but a lot of people in, let's say, in the group at large connected to us are working on that. So I don't see Antoine connected there, but Antoine is a French that's an internship in our group in Argentina. He's starting to work on the machine learning classification part. And for LSST, there are a lot of suggestions on machine learning, with crazy ideas, like, for example, using generative models, using new nets to make masks to then make the modeling. So there are a lot of ideas to discuss, which may be just ideas and it's nice to share, or maybe actual projects on which we can work together. So there is also a specific slot on that, on the machine learning side. So please come and join these discussions. So yes, Thursday is the hands-on day. We have 3 hands-on. We have on the Raspberry, so it's the database, how you query, how you use it, maybe how you build it too. The code is all on GitHub. Then there is the hands-on on the Raspberry tagging and vetting, which is clicking and quite additive. So if you have a tendency of being addict, maybe I don't recommend it to you. And then there is the hands-on on the regression and some discussions. So this is Thursday, and Friday, the meeting. But the idea was to have a fully open meeting. If there are people that are here or online, that they have common interests and they want to get together for whatever reason at whatever time, we have space at CBPF, right? Of course, this is not a massive meeting and not people from a lot of places, so that may not happen. So, but if that happens, so if you are interested in having a parallel meeting besides what's in the program, joining more than one person, it's enough. Just let me know during the holiday, so until tomorrow, May 1st, that, hey, I want a meeting room to meet with my student that is in, I don't know, Olinda and has come to here and I want to talk to him, or whatever reason. Tell us, because we have this space reserved. We have a couple of space reserves. If no one asks, and if it's totally fine if there is no such a demand, but if no one asks, then we'll free all these rooms that we have reserved for Thursday and Friday. That's the only thing. So the central place is still here. Thursday, Friday, you have the program. This room is the central place. The coffee break will always be there at that time. So if you're not attending what's going on here, if you're attending a parallel thing, come and meet us in the coffee moment so that we can talk. And after the hands-on of tomorrow, then it's pure discussion. So it's not broadcasted, it's participation through Zoom. Yeah, I think that was the organizational message I wanted to pass on. So any comments and questions about that?
I would only comment that I cannot believe someone could be addicted to to tagging lenses unless they can bet on it, right? Which could be an opportunity for funds in science, right? People are crazy betting about everything you might ever believe. Anyway, so any other comments, people?
Yeah, so I have a question basically to Martin. So what are the plans to share the last Beru data with the scientific community? Because as of now, if I understood well, the last Beru is only on available on Chi, right? So the idea is to build a dashboard, a website where everyone can access and so on. What are the plans? Can you comment?
Yeah, that's the idea. Like Renan has set up such a framework at the beginning, like a server serving the data. You could query, etc. Then it went down for some reason. So I don't know. We'll hear from him on Thursday. But yes, the idea is to have this like a server serving this data for the community and the code on GitHub. So when you publish the paper, all will be available. But what I think is the real, so this is like, okay, we give this to you. But what I think is the real solution is the sustainability of this. So that's being discussed in the Strong Lensing Science collaboration of the several efforts and how we get together and how we make this. So ideally, I think we should have a framework which goes beyond Las Peru, beyond SL Comp, but beyond the things other people have been doing, and having like a community service where we have a server, someone is responsible for it, you know, pays, etc., etc. So I think we should aim at that. I think thinking about the LSST, I think that should be a goal of the Strong Lensing Science collaboration, to be able to maintain this. It doesn't need to be one central system, can be two, can have copies, blah, 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 but something that it's not, I mean, there has been a nice service to the community, which is the Orphan Lenses project, but it suffered clear from the sustainability thing, that it's a nice framework, people can feed information in, but it seems that like the community sort of didn't follow. So that needs to be something that it's not effort of someone to be something static, but rather it involve a lot. Of course, the fact that you expect 100,000 systems makes a lot of interest in having something more professional. Also, the fact that people want to have these lookup tables for many things, like lensed gravitational waves or lensed transients and so on. So I think it's a good moment to find a longer term solution. I don't claim SL Comp or Las Beru are the longer term solution. I think we have a philosophy of doing things, which I do think it's very, very useful. So I think in terms of concepts, I think we are doing something that's quite different and maybe more comprehensive than other things. But on the technical side, I think we are doing very basic stuff. So really we should get together. People are doing more sophisticated things in the technical side with all these views that different people have, and try to have a framework where we can get. I don't think that's is this framework, but replying to your question again, yes, we'll make the catalog available with this interface that Renan has set up for querying as an intermediate step towards something bigger, larger, longer term thing.
Okay, thanks.
Any other comments, questions? Or everyone is as hungry as me? People online might already having lunch. That's what I do. I turn off my camera. Anyway, no pressure. All right, so let's call it the meeting. This morning session. The discussion today? No, only tomorrow, right?
Today's over.
Today,
Tomorrow
only
we are
tomorrow.
back at 9.
Okay. So I guess I see you all tomorrow. Thank you very much. Let's thank the speakers again.
Happy lunch and see you tomorrow. Oh, Christina. Oh, yes, she's clapping.
Bye, thank you.